Welcome to Night Cosmos Sleep. Tonight, we are traveling to Mars, not to ask whether humans can set foot there, but to explore what happens after that first footprint has already been made. Because landing on a planet and surviving on it are two entirely different challenges. Imagine an astronaut standing at the hatch of a lander. Just a few inches beyond them lies the surface of Mars, yet the door cannot open until the pressure, oxygen, supply, batteries, communications, and suit seals have all been checked. Before stepping outside, that person must carry everything the human body needs to remain alive. The spacesuit is more than protective clothing. It is a miniature living environment, preserving the air, temperature, and pressure the body requires. When the astronaut steps onto the ground, they are not truly coming into direct contact with Mars. They are moving inside a tiny fragment of Earth carried with them from home. When they return to the base and remove the suit, that dependence does not end. The artificial environment simply expands from a shell around the body into an entire living space. Air must keep circulating, water must be recovered, temperature must remain controlled, and waste gases must be removed without interruption. From the outside, the base may resemble a home. Inside, however, it is a machine that cannot be allowed to stop. If one critical component fails, the result is more than inconvenience, because the most basic needs, breathing, drinking water, staying warm, and sleeping safely, may all be affected. On Earth, human beings live within an enormous natural life support system. The atmosphere surrounds our bodies, water cycles continuously, soil nourishes plants, and ecosystems process countless things we rarely have to think about. On Mars, nearly all of that work must be replaced by machines. Living on Mars, then, is not simply a matter of building a shelter on new land. It means creating a miniature Earth, keeping it running without interruption, and repairing it in a place where help from home may be hundreds of millions of kilometers away. Every breath, every drop of water, and every meal becomes part of the survival system. The question that will follow us throughout this journey is this: if everything keeping humans alive is created by technology, are they truly living on Mars, or are they simply living inside a spacecraft that has landed on its surface? To find the answer, we must first look at the earliest boundary every person arriving on the red planet will have to face. Outside the base, a thin veil of dust is slowly drifting across the ground. The red grains are so small that each one is nearly impossible to see. Yet their movement reveals that Mars is not entirely silent or still. This world has air, wind, wispy clouds, and weather patterns that change with the seasons. But the presence of an atmosphere does not mean that atmosphere can sustain human life. An astronaut stands a short distance from the base, watching dust gather around their boots. Their body is surrounded by a sealed layer of gas held inside the suit, while just beyond that protective material lies the true atmosphere of Mars. The two environments are separated by only a few inches, yet they could hardly be more different. One allows the blood to keep carrying oxygen to the brain, heart, and muscles. The other is too thin, too cold, and contains far too little oxygen for the body to survive in it, even briefly. The Martian atmosphere is composed mainly of carbon dioxide, along with small amounts of nitrogen, argon, and other gases. Oxygen is present, but in quantities far too low for humans to breathe directly. This is not like standing in a polluted city, where a mask can filter out particles while allowing air to pass through. On Mars, a mask cannot create something that is barely there. To survive outside the base, a person must carry both the oxygen they need and the pressure required for their lungs to function. On Earth, our bodies are always submerged beneath an invisible ocean of air. The gases surrounding the planet have weight, and that weight creates a constant pressure against every surface. We do not notice it because the human body formed and evolved under those conditions. Our lungs, blood vessels, eyes, skin, and internal fluids all depend on the quiet, continuous presence of atmospheric pressure. On Mars, that ocean of air has almost entirely drained away. The average surface pressure is only a small fraction of what we experience at sea level on Earth, although the exact value changes with elevation, season, and weather. The air is still capable of pushing dust across the ground, but it is not dense enough to protect the human body. It is more like a faint haze of gas surrounding the planet than the deep atmosphere we live within every day. If a suit loses pressure, the body would not explode as science fiction often suggests, nor would a person instantly freeze into a block of ice in the middle of the red desert. The first danger is that the lungs can no longer exchange gases under the conditions they require. Oxygen levels in the blood fall rapidly, and the brain begins to lose its ability to function. When pressure drops low enough, fluids on moist surfaces such as the eyes, mouth, and airways may also begin to boil, even though the temperature is not high. The severity of the injury would depend on the remaining pressure, the duration of exposure, and how quickly the person could be returned to a properly pressurized environment. A large tear in the suit might create an obvious emergency, but sometimes the more troubling threat is a leak too small to notice. Gas may not escape with a violent blast. Instead, it can slowly seep away through a joint, seal, or worn surface. The astronaut may feel nothing unusual while the reserve supply is quietly shrinking with every passing minute. For this reason, a pressure suit must perform many tasks at once. It supplies oxygen to the wearer, removes the carbon dioxide the body exhales, keeps pressure within a safe range, and controls the moisture building up inside. A cooling system must also carry excess heat away from the body, because even in an extremely cold environment, someone working inside layers of sealed material can overheat very quickly. The suit must not only keep Mars out, it must continuously manage everything the human body produces within it. This creates a strange paradox. An astronaut may be standing in a world far colder than Earth and still require active cooling. Under direct sunlight, the surface in some regions near the equator may occasionally reach temperatures that do not feel impossibly cold by human standards. But that is only the temperature of soil or rock absorbing sunlight. It does not mean the surrounding air has become warm, comfortable, or safe to live in. The Martian atmosphere is too thin to retain heat effectively. As sunlight fades, warmth stored in the surface quickly escapes, and temperatures can fall dramatically after sunset. The same location may experience a wide swing between day and night, forcing the base and every piece of equipment outside to endure repeated cycles of heating and cooling. For humans, this means that heating systems are not simply a matter of comfort. They preserve the conditions that allow water, batteries, pipes, and medical equipment to keep functioning. These daily temperature changes also place a quiet strain on materials. Metal frames, habitat walls, airlocks, seals, and joints do not all expand and contract in exactly the same way. When one section changes size more quickly than the one beside it, small forces develop where the materials meet. A single cycle may cause no visible problem, but after hundreds or thousands of repetitions, a tiny crack can begin to form. A failure, then, may not appear on the first day or even during the first month. A base may operate normally for a long time before a seal begins to lose its flexibility or a joint develops a gap too small to see. From that point on, air may escape more slowly than human senses can detect. Pressure sensors, inspection routines, and the regular replacement of components become matters of survival, even though they may seem far simpler than launching a spacecraft between planets. The thin atmosphere also changes the way water behaves on the surface. Ancient Mars once had rivers, lakes, and bodies of water that lasted long enough to carve valleys and create minerals that form only in wet environments. Those traces remain in the landscape, but the modern planet is very different. Low pressure and cold temperatures prevent liquid water from remaining stable across most of the surface, so the water that remains is found mainly as ice, locked inside minerals, or hidden beneath the ground. This does not mean that every drop of water would vanish the instant it was carried outside. The rate at which it freezes, boils, or evaporates depends on temperature, pressure, and chemical composition. Certain salty solutions may persist briefly under unusual conditions, but they do not form rivers, lakes, or open reservoirs that humans could easily use. Water returns to the familiar state we know only when it is brought into an environment where machines maintain the necessary pressure and temperature. Inside the base, a glass of water can rest quietly on a table just as it would on Earth. Beyond the wall, that same amount of water becomes difficult to keep stable. The boundary between those two conditions lies within the habitat shell and the environmental control systems operating behind it. Once again, the most ordinary things become ordinary only after humans recreate a small part of what Earth's atmosphere silently provides every day. Nowhere is this difference more visible than in the airlock. It is a small chamber connecting the pressurized living area with the unbreathable environment outside. Each time an astronaut passes through, the two doors must never be opened at the same time. The chamber has to be sealed, its pressure changed in stages, leaks checked, and any dust clinging to the suit or tools carefully monitored. When the design allows it, some of the remaining air may even be recovered rather than released outside after every excursion. During a mission lasting many years, the airlock would not be used only a handful of times. It might have to open and close through thousands of cycles as the crew explores, repairs equipment, extracts resources, and maintains systems on the surface. Every movement adds wear to the hinges, seals, valves, and sensors. A rocket engine only needs to operate during certain phases of a mission, but an airlock must continue working for as long as the base remains inhabited. If this system fails, the crew could become trapped on either side. Anyone outside might be unable to return, while those inside could lose access to essential equipment on the surface. For that reason, an airlock needs multiple operating modes, a way to be opened manually, and rescue procedures that have already been practiced. It is not merely the entrance to the base. It is the mechanical boundary between a livable world and an environment that cannot sustain the human body. Even the location of the base is influenced by the thin atmosphere. Low-lying regions may have slightly higher pressure than the highlands, but the difference is still nowhere near enough for humans to breathe. Areas near the equator generally receive more sunlight and experience more favorable temperatures, yet they may lie far from accessible water ice. Higher latitudes, by contrast, may contain more ice close to the surface, but they are colder, darker during certain seasons, and more difficult to reach safely during landing. No site would be chosen simply because the landscape is beautiful or because it lies near an appealing scientific target. Mission planners must balance elevation, temperature, sunlight, terrain, dust, distance from water ice, and communication access. A flat region well suited for landing may not contain enough useful resources. A site rich in ice may place greater demands on heating and power systems. Every advantage comes with a different engineering cost. In this way, the atmosphere becomes a background condition shaping nearly every decision. It is too thin to breathe, poor at retaining heat, unable to keep liquid water stable, and forces the base to maintain a much higher pressure than the environment outside. At the same time, it is still dense enough to produce wind, clouds, dust, and weather. Mars is not an entirely empty world, but the processes unfolding in its atmosphere are not suited to a body that evolved beneath the skies of Earth. The astronaut outside the base can still see dust sliding across the ground. That movement is a reminder that the planet has air, yet the layer of gas surrounding the entire world cannot provide even a single safe breath. To survive, humans must create an atmosphere of their own inside the suit, within the airlock, and throughout every room of the habitat. From the moment they step onto the surface, life depends on their ability to hold a small amount of gas in place on a planet that is always ready to let it escape. But even if the walls maintain pressure and the base produces the right mixture of gases, they still cannot completely block everything arriving from space. Some particles are far smaller than dust and carry enough energy to pass through materials and enter living tissue without causing any immediate sensation of pain. They do not force the airlock open, cause the habitat to lose pressure, or leave behind marks that are easy to see. To understand why a sealed shelter is still not entirely safe, we must leave behind the thin air of Mars and turn our attention to the space above it. There, an invisible rain continues to fall toward the surface, carrying particles from the sun and from far more distant regions of deep space. Morning begins inside the base without any sign that something is wrong. The crew wakes, checks the systems, and prepares for work on the surface. No alarms sound, the sky does not change color, and no one feels any pain. Yet on the monitoring screens, sensors are quietly counting each energetic particle passing through the outer shell of the habitat. Radiation has no smell, makes no sound, and usually produces no immediate sensation when exposure occurs. A person may eat, talk, and complete an entire day's work, while the body continues to receive tiny additional doses. That invisibility makes radiation harder to imagine than cold, dust, or a loss of pressure. While other dangers leave obvious signs, radiation may appear only as numbers slowly rising on a screen. On Earth, most of us rarely have to think about the high-energy particles moving through space. Our home planet is protected by a thick atmosphere and a magnetic field that surrounds the globe. The atmosphere absorbs or weakens many forms of radiation before they can reach the ground, while the magnetic field deflects some of the charged particles arriving from the sun. These two layers of protection do not block all radiation, but they greatly reduce exposure where humans live. Our bodies evolved beneath that shelter over an immense span of time. Mars, however, has no comparable global magnetic field, and its atmosphere is far too thin to provide the same level of protection as Earth's. As a result, the surface of the red planet exists within a very different radiation environment. Some regions of Mars still contain traces of magnetism locked within the ancient crust, but these fields are local and do not form a shield around the entire planet, nor is there enough air above the surface to stop most of the energetic particles descending toward it. Even when an astronaut stands beneath a quiet sky, the space overhead is continuously sending down particles that the human eye cannot see. The first source is galactic cosmic radiation, made up of high-energy particles arriving from beyond the solar system. These particles are present almost continuously and can carry enormous amounts of energy. Some penetrate deeply into materials, passing through spacecraft walls, habitat structures, and even the human body. There is no clear moment marking their arrival because they are a permanent feature of the deep space environment. When these particles collide with matter, they can ionize atoms and produce additional secondary particles. Shielding them is therefore not as simple as placing a very thick sheet of metal in their path. A wall may reduce part of the radiation flow, but it may also become the site of new collisions. The crew must accept that this background radiation can be limited, but is extremely difficult to eliminate entirely. The other source comes from the sun. Most of the time, energetic particle levels do not rise suddenly enough to create an emergency. But when the sun releases powerful streams of particles, the environment around Mars can change quickly. The crew may then need to stop all outdoor activity and move into a more heavily shielded area, even though the sky before them still appears completely normal. These two radiation sources create different kinds of danger. Galactic cosmic rays produce prolonged exposure that humans can never fully avoid. Solar particles, by contrast, may arrive in intense bursts and raise the dose over a shorter period. One source must be managed throughout the entire journey, while the other requires warning systems and the ability to respond quickly. Much of what we currently understand comes from the radiation assessment detector aboard the Curiosity rover. This instrument measured radiation during the journey from Earth to Mars and continued operating after Curiosity landed in 2012. Its data has helped researchers estimate the environment a crew might encounter both during interplanetary flight and while living on the surface. The measurements show that a flight to Mars is not merely time spent traveling between 2 points. During the many months spent beyond most of Earth's magnetic protection, the body remains continuously exposed to cosmic rays and solar particles. Depending on the mission design, time aboard the spacecraft may contribute a substantial portion of the total dose, sometimes as much as the period spent on the planet itself. Some mission models have estimated that the total dose from a round trip lasting several years could approach 1 sievert. This is not a fixed value for every journey, because exposure also depends on the launch date, solar activity, flight path, and length of the surface stay. The spacecraft's structure, shielding materials, and the way the crew uses different areas inside it can also change the result. Receiving a significant radiation dose does not mean that every astronaut will inevitably become ill. Risk is measured in probabilities and may differ from one person to another. Age, biological sex, body composition, total exposure time, and the sensitivity of different tissues can all influence long-term consequences. 2 people living in the same base may still face somewhat different levels of risk. The concern is not always an injury that appears immediately. Energetic particles can produce small changes within cells and DNA that gradually accumulate over months or years. Over time, these changes may increase the risk of cancer, cataracts, damage to the nervous system, and other health problems. A person may continue to feel perfectly normal while those effects are quietly developing. There is no single moment when anyone can say that the damage has begun. The total dose accumulates through every day spent in space, every hour worked outside the habitat, and every period of intense solar activity. Protecting human health, therefore, cannot begin only after the spacecraft lands. It must be considered in the spacecraft's structure, the placement of supplies, and the amount of time each person is allowed to spend on the surface. On the 20th of May 2024, Curiosity recorded the largest radiation spike detected since the rover landed. NASA estimated that a person standing beside Curiosity at the time could have received about 8,100 micrograys, roughly equivalent to nearly 30 chest X-rays. This was a significant level, but not a dose that would immediately kill a person or turn the entire Martian surface into a deadly zone within minutes. That event shows that the danger does not need to be exaggerated in order to be serious. A powerful burst may not cause an immediate catastrophe, but it can still add to the total dose and force the crew to change its plans. Outdoor work must stop, anyone far from the base must return, and non-essential activities may be postponed until the environment becomes more stable. When a warning appears, the crew would move into a small compartment near the center of the base. Surrounded by more material than ordinary living areas, this space would serve as a shelter during periods of intense energetic particles. It would not need to be spacious or comfortable, but it would require ventilation, water, communications, and enough life support to keep the crew safe until the danger had passed. Water tanks, food, equipment, and stored supplies could be arranged around the shelter. Items originally carried for everyday use would then become part of the shielding. Water is especially useful because it contains large amounts of hydrogen, which can reduce the effects of certain particles more effectively than many heavier materials. Hydrogen-rich plastics such as polyethylene could also be incorporated into the design. The arrangement of supplies would therefore become more than a matter of saving space. Aboard the spacecraft traveling to Mars, water, food, and other materials could be positioned around sleeping areas or emergency shelters. A container placed in the right location would not only remain accessible when needed, but could also help reduce the amount of radiation reaching the body. Logistics would become part of the medical strategy. After landing, Martian soil could provide additional shielding without requiring all of the material to be transported from Earth. Robots might excavate the soil, place it over the roof, or pile it around modules designed to support the added weight. This layer would help reduce radiation while also moderating some of the temperature changes between day and night, turning the planet's own surface into protection for the people living beneath it. Covering a base with soil, however, would not be a simple task. The structure would have to withstand the additional mass, while the robots used for digging and transport would require power, spare parts, and regular maintenance. The soil could not be allowed to block radiators, obstruct emergency exits, or damage the pressure shell. A solution that reduces the amount of material carried from Earth creates another chain of machines that must be kept operational. Natural terrain might also become part of the shielding. Cliffs, deep depressions, or suitably located lava tubes could reduce radiation exposure and maintain more stable temperatures than a habitat built entirely on the open surface. Constructing a base beneath layers of rock could significantly reduce the amount of shielding material that must be transported from Earth. In return, complex terrain would make landing, transportation, and communication more difficult. A well-shielded location might not be suitable for a lander or close to accessible water ice. Natural cavities would also need to be carefully surveyed for falling rocks, collapse, and geological conditions that are not yet fully understood. Every natural layer of protection would bring a new kind of risk. Even with abundant material available, simply building thicker walls does not always produce greater safety in a straightforward way. When high-energy particles collide with heavy metals, they can generate many secondary particles that continue traveling deeper inside. In some cases, choosing the wrong material can make the radiation environment behind the shield more complex, rather than steadily reducing exposure. An effective design must combine several protective measures: water, polyethylene, Martian soil, the placement of different compartments, and the distance between people and the outer surface all play distinct roles. Alongside physical shielding, work schedules must also be adjusted according to space weather data. The crew may reduce time spent outside during periods of elevated risk and rely on robots for tasks that do not require direct human involvement. Each person may carry an individual dosimeter to record their exposure throughout the mission. This information can help distribute assignments and prevent one crew member from receiving a much higher dose than the others. If someone has already spent considerable time on the surface, another person may take their place during later excursions. The health of the crew becomes a resource that must be allocated with care. However, watching the radiation dose rise day after day may also create psychological pressure. Astronauts cannot directly sense when a particle passes through their bodies, so they must rely on sensors and calculated models. A rising number does not mean illness is certain to appear, but neither can it be ignored. That uncertainty may follow them through their working hours and into their periods of rest. To prevent radiation from becoming a constant source of fear, exposure limits must be explained clearly from the beginning. The crew needs to know which levels allow work to continue, when they must return, and when they need to enter the shelter. The information should be detailed enough for them to understand the danger without forcing each person to interpret complex data while under stress. A clear procedure transforms an invisible threat into something that can be managed. No matter how carefully the mission is prepared, humans cannot completely eliminate the radiation environment on Mars. Soil, water tanks, shelters, and work schedules can only reduce the dose. A mission lasting several years may manage the danger in one way, but a community hoping to survive for many generations would face a much greater challenge. The longer people remain, the more important their total accumulated exposure becomes. Inside the base, the sensors continue counting every particle that passes through the outer shell. The crew cannot hear them or feel any pain, yet the invisible stream of energy influences every decision about where they sleep, how long they work, and where the water tanks are placed. If the instruments stop functioning, the radiation does not disappear. Humans simply lose the ability to know how the danger is changing. Outside, red soil may be piled over the roof to protect the people living beneath it. Yet after every excursion, that same soil clings to boots, gloves, and the joints of the spacesuits. A material can serve as a shield while it remains outside the base, but it may create new problems when its smallest particles follow people through the airlock. From the surface, dust will cling to equipment, settle into narrow gaps, and find its way toward the filters, keeping the air clean. It does not need to pass through the walls as radiation does, because humans themselves will carry it home every time they venture outside. From the moment the airlock closes, a new threat has already entered the habitat. After spending several hours surveying the surface, an astronaut returns to the airlock. The suit, once light in color, is now covered in a thin red layer, most visible around the knees. Gloves, boots, and joints that move repeatedly. Toolboxes, rock sample bags, and equipment wheels carry similar traces of dust. The door closes behind them, but a small part of Mars has entered with the crew. The tiny particles clinging to every surface are not simply dry soil in the familiar earthly sense. Over immense periods of time, they have been ground down by impacts, wind, and repeated cycles of heating and cooling in an environment with almost no liquid water or modern biological activity. There is no frequent rainfall to soften the edges of the grains, nor are there plant roots and organic matter to create the loose, gentle soil found across much of our home planet. Martian dust may therefore differ in shape, size, and composition from the dust people normally encounter indoors or along a road. A single grain may seem insignificant, but millions of them can enter narrow gaps, cling to surfaces, and scrape against moving parts. For the habitat, mechanical damage may sometimes appear long before any chemical effects on human health. When a joint in the suit bends, dust trapped between layers of material can act like a microscopic abrasive. Each movement creates only a tiny scratch, but thousands of repetitions gradually wear away the smoothness of the surface. The same process can affect hinges, bearings, locks, connectors, and every mechanism that must operate each day. Mars does not need to destroy a piece of equipment all at once. It only needs to leave dust in place for long enough. The dry environment can also cause particles to become electrically charged and cling tightly to equipment. They settle over cameras, sensors, radiators, electrical connectors, and areas that cleaning tools cannot easily reach. A brush may remove the visible layer, yet smaller particles remain inside grooves or quickly attach themselves again. Cleaning, therefore, is not as simple as brushing dirt from a pair of boots. There is no need to assume that every dust storm produces enormous bolts of lightning or immediately causes fires and explosions. The more realistic danger lies in slow accumulation and the possibility of distorted equipment readings. A thin layer of dust on a sensor may reduce the accuracy of its measurements, while dust coating a radiator may alter the way machinery releases heat. When several small irregularities appear at once, the crew must spend additional time determining which signals indicate a genuine failure and which are merely the result of dust. The chemical composition of the surface material raises another question. Mars missions have detected perchlorates, a group of oxidizing salts. If they enter the body in sufficient amounts, they may create health problems and complicate the treatment of water, agricultural soil, or materials brought into the habitat. This does not mean, however, that every grain of dust is immediately toxic. The level of danger depends on concentration, particle size, duration of exposure, route of entry, and the specific composition at the chosen base site. A particle resting on the outside of a suit is different from one drawn deep into the lungs, just as a few minutes of exposure is entirely different from living in that environment for years. Any assessment must be based on the amount of dust that actually enters the living area, not merely on the presence of perchlorates in the soil. The greatest gap in our knowledge is that no authentic Martian dust sample has yet been returned to Earth for comprehensive respiratory and toxicity testing. Most of what we currently understand comes from rover instruments, mineral analyses, simulated Martian materials, and experience with similar compounds. These sources provide enough information to establish preliminary limits, but they cannot yet describe every response the human body may have after prolonged exposure. In July 2026, a NASA assessment suggested that a conservative continuous 30-day exposure limit for particles smaller than 10 micrometers would be about 0.1 milligrams per cubic meter. This value includes a large safety margin because direct evidence remains limited. It is not an absolute dividing line between safety and danger, but a temporary control level while science continues working to understand the dust more fully. When dust enters the base, larger grains may quickly settle onto the floor or be collected in the cleaning area. Smaller particles, however, can remain suspended in the air for longer periods, follow the ventilation flow, and eventually be inhaled. Some may be trapped in the nose or upper airways, while the finest particles may travel much deeper into the lungs. The eyes and skin are not entirely protected once the suit has been removed. Dust may cause irritation if it gathers around the eyelids, enters broken skin, or remains on gloves and medical equipment. Inside a sealed habitat, even a small amount that is not collected properly may continue moving from one surface to another. Control must therefore begin at the airlock, before the particles have a chance to spread into the living spaces. The length of a mission completely changes the scale of the problem. A survey lasting only a few days involves a limited number of excursions, but a base operating for years may support thousands of journeys across the surface. Every return brings in a new quantity of dust, no matter how effective the cleaning procedures may be. The risk comes not only from a single large exposure, but also from extremely small amounts repeated without interruption. One way to reduce contamination is to avoid bringing the entire suit inside. Instead of putting it on and removing it within the habitat, an astronaut could enter through a port attached directly to the outer wall. Most of the dirty surface would remain outside while the wearer climbed in through the back. This design could limit the amount of dust passing through the airlock and reduce the need to clean the entire suit after every use. The connection port, however, would have to remain airtight through a great many cycles. Its seals would be exposed to dust, temperature changes, and repeated movement, while the locking system would still need to function after some degree of wear. If either the suit or the hatch failed, the crew would need a way to bring the astronaut back inside without losing pressure. A solution that reduces dust also creates additional components that cannot be allowed to fail. The base should not depend on a single boundary between the surface and the living area. The outermost zone could receive suits, tools, and collected samples. A middle zone could be used for cleaning, inspections, and changing protective layers, while the innermost area would remain cleaner for sleeping quarters, the kitchen, and medical facilities. Dividing the habitat into several layers would force dust to pass through multiple barriers before reaching the places where humans spend most of their time. Airflow could be directed from cleaner zones toward dirtier ones rather than in the opposite direction. This would make dust less likely to be drawn deeper into the habitat whenever doors between sections are opened. Filters in the outer area would carry a heavier load and require more frequent inspection. Ventilation design would no longer serve only to provide oxygen. It would also create a controlled direction of travel for unwanted particles. Cleaning procedures could combine brushes, air currents, vibration, non-stick surfaces, and electrostatic forces. Each method would be suited to different locations and particle sizes. Brushes could remove thick layers of dust but might scratch the material, while streams of air could easily send smaller particles back into circulation. Electrostatic forces might repel dust from certain surfaces, but they would require electrical power and specially designed systems. No single method is perfect for the entire base. An effective system must remove enough dust without creating even smaller particles, damaging the outer layers of the suits, or consuming too many supplies. Every cleaning cycle uses electricity, time, and some of the equipment's service life. Even the work of keeping the habitat clean becomes another chain of dependence that must be maintained. Outside the living quarters, dust continues to settle over equipment that cannot be brought indoors. Solar panels are among the surfaces most vulnerable to its effects. When sunlight must pass through a layer of dust before reaching the photovoltaic cells, power output declines. A thin coating on each panel can become a serious problem when the entire energy system loses efficiency at the same time. Winds on Mars may occasionally clear part of a surface, as they once did for several rovers. But a base cannot build its survival plan around unpredictable natural cleaning events. Robots, tilted panel designs, dust-resistant coatings, and vibration systems may help, yet every solution introduces additional motors, sensors, and software that must be maintained. If a cleaning robot stops working, humans may have to go outside and handle the task manually. That increases radiation exposure, consumes more oxygen, and creates another occasion for a suit to carry dust back inside. A problem that begins on a solar panel can spread into the health, energy supply, and work schedule of the entire crew. In a closed environment, dust rarely affects only one system. Particles trapped inside seals may be even more dangerous than the visible dust covering a surface. A single grain in the wrong place can prevent two faces from making complete contact, creating a tiny leak. At first, the pressure may remain within acceptable limits, but the hard particle will scratch the surface each time the door opens and closes. After many cycles, that scratch may become a path through which air slowly escapes. Cleaning, camera inspections, pressure testing, and the scheduled replacement of seals must therefore become part of daily life. These tasks may not seem as exciting as driving a rover or collecting rock samples, but they directly determine whether the base can continue holding its atmosphere. On Mars, an inexpensive seal may be more important than many costly scientific instruments. Inspections must also take place before any sign of leakage appears. By the time sensors detect a pressure drop, the surface may already have been damaged for quite some time. Preventive maintenance allows components to be replaced while there is still enough time and a safe place to work. This requires the base to carry sufficient spare parts and tools, along with records tracking the service life of every component. Dust is not the only thing that accumulates inside a sealed environment. Humans bring bacteria, fungi, and many microbial communities living on the skin, in the digestive tract, and on personal belongings. They cannot be completely removed before launch, nor should they be considered entirely harmful. Many microorganisms play important roles in digestion, health, and the biological cycles that may help the base function. Even so, damp surfaces, filters, and water lines can become places where microbes grow unintentionally. A small patch of condensation behind a wall panel may remain hidden for weeks. If dust provides additional minerals or creates a surface to cling to, microbial communities may develop in places that are difficult to clean. Air quality then depends not only on filtration, but also on controlling moisture. Excessive sterilization cannot turn the habitat into a place entirely free of microorganisms. Strong chemicals may also accumulate in the air, damage materials, or eliminate beneficial species, along with harmful ones. The goal is not to create an absolutely sterile environment, but to maintain a monitored and balanced microbial ecosystem. The base must remain clean enough to protect human health, while still supporting bodies that naturally live alongside microorganisms. This makes dust management part of a miniature ecological problem. Particles from outside, microbes from the human body, moisture from breathing, and chemicals released by equipment all meet within the same enclosed space. None of these factors can be managed entirely on its own. A filter that traps dust may also become a place where microbes grow if it is not replaced or dried properly. Each time the airlock opens, the boundary between Mars and the living quarters becomes slightly less absolute. The planet does not rush inside with a powerful gust of wind. Instead, it leaves traces on gloves, wheels, and rock samples carried into the laboratory. Most of the dust may be contained in the outer zone, but no system can guarantee that every particle will be removed. Life becomes a continuous process of controlling what is allowed to cross the boundary. Humans cannot solve the problem simply by sealing the base and never going outside. They still need to inspect solar panels, repair pipes, extract ice, collect samples, and expand their living space. Robots may reduce the number of excursions, but robots also require maintenance, and sometimes humans must go outside to repair them. The base can survive only by maintaining contact with the surface, even though every interaction carries risk. Once the suit has been cleaned, the astronaut passes through the innermost zone and returns to the living area. Most of the red dust has been left behind. The filters continue collecting the particles still suspended in the air, and sensors confirm that concentrations remain within acceptable limits. No one can know exactly how many tiny grains have passed through every barrier, but the system must keep that number as low as possible. Dust can be swept from the floor, trapped inside filters, and kept away from the sleeping quarters. Yet one feature of Mars does not cling to a suit and cannot be stopped by an airlock. From the moment the spacecraft touches the ground, every object, every machine, and every cell in the human body begins to experience a new gravitational pull, only a little more than 1/3 of what is familiar on Earth. This change triggers no alarm and leaves no red coating behind. It quietly alters the way humans stand, walk, lift heavy objects, and maintain their balance, then continues affecting their bones, muscles, heart, and circulation day after day. The question is no longer whether the body notices the difference, but whether 0.38 G is enough to keep a human being healthy for many years. After drifting in near weightlessness for many months, an astronaut rises from the spacecraft seat and tries to stand on their own legs. The body has just passed through a period in which it no longer had to resist the familiar downward pull, and now it must maintain balance under a new gravitational force. The astronaut feels far lighter than on Earth, yet can no longer float freely as they did during the journey. Each step carries them farther than expected, while stopping or changing direction requires a level of concentration that the body once managed almost automatically. Gravity at the Martian surface is only about 38% as strong as Earth's. A person with a mass of 70 kilograms would feel considerably lighter, but their actual mass has not disappeared. The body still contains the same amount of matter, and every object retains its inertia. Mars makes things easier to lift, but it does not make them easier to control in every situation. A large cargo container may require less effort to raise from the ground, but once it begins moving, it still tends to continue in the same direction. If an astronaut pushes too hard, the load could pull them off balance or collide with nearby equipment. Inside a suit that restricts movement and narrows the field of vision, a single poorly judged step may be enough to cause an accident. Lighter does not necessarily mean safer, because weight is reduced while momentum remains. The first few hours after landing may be the most difficult. Astronauts do not step onto Mars with bodies as strong as they were when they left Earth. Months in microgravity may have weakened their muscles, reduced mineral density in their bones, and change the way their circulatory systems regulate blood pressure. These processes still occur even when the crew exercises regularly during the flight. Just before touchdown, the body must also endure the acceleration of descent and landing. Afterward, the astronaut must put on a suit, leave the spacecraft, move down a ladder, and remain ready to respond if anything fails to go according to plan. All of this happens while the balance system is relearning how to interpret gravitational signals. A task that appears simple may become difficult because the body has not yet adapted to its new environment. Bone is one of the systems that responds most clearly to changes in mechanical loading. Bones are not motionless structures formed once and preserved unchanged throughout life. Bone tissue is continuously broken down and rebuilt according to the forces the body experiences during everyday activity. When those forces decrease, the body may interpret this as a sign that it no longer needs to maintain the same amount of tissue. In microgravity, bone loss may occur faster than new bone can be formed. Areas that normally bear weight, including the hips, legs, and spine, are especially important because they play a major role when humans return to an environment with gravity. Mars provides a clear downward pull and may therefore be far better than complete weightlessness. Yet no one knows whether 38% of Earth's gravity is enough to preserve a healthy skeleton over many years. Data from orbital missions confirms that reduced mechanical loading is a genuine danger, but it cannot provide a direct answer about Mars. Microgravity removes nearly all continuous weight-bearing forces, while 0.38 g still requires the body to stand, walk, and carry objects. That level of gravity may slow physical decline, prevent some of it, or remain insufficient for certain tissues. The difference between those possibilities can only be clarified through long-term data that humans do not yet have. Muscles change in a similar way. On Earth, the muscles in the legs, back, and core work continuously to maintain posture, support walking, and resist the downward pull of gravity. Even while a person stands still, many muscle groups remain active. When gravity decreases, the body tends to conserve energy by reducing tissues that are no longer being used with the same intensity. Astronauts would still move around, repair equipment, and work on the surface. But these activities would not guarantee that every muscle group received enough stimulation. The suit might assist certain movements while restricting others. Walking on Mars would also differ from walking on Earth, so traveling the same distance would not produce the same pattern of physical activity. Some muscles might work harder, while other essential groups would continue to weaken. To resist this process, the base would need resistance training equipment, stationary bicycles, and a system that allows astronauts to run under low gravity. Cords or elastic mechanisms could pull the body toward the floor, increasing the load on the legs and bones. Exercise would need to be intense enough to provide a meaningful stimulus without injuring someone who had just spent many months in microgravity. It would also have to be adjusted for each individual, rather than applied at the same level across the entire crew. Exercise time would not be an optional break, but part of the daily work of staying alive. Astronauts might need to devote a significant portion of each day to maintaining their bodies, even when schedules are already crowded with repairs, research, and surface exploration. Missing several days of exercise might not produce immediate symptoms, but the decline would accumulate if it happened repeatedly. On Mars, keeping the body functional would have to be managed much like maintaining machinery. The exercise equipment would create demands of its own. Each machine would need to be compact enough to fit inside the habitat, produce little enough vibration to avoid damaging the structure, and remain durable through thousands of uses. Cables, bearings, and load-bearing components would all wear down over time. If an essential machine failed, the crew could not simply order a replacement and wait for it to arrive. Outdoor work might help preserve physical fitness, but it could not completely replace a controlled exercise program. Moving around in a spacesuit requires energy, yet the suit limits motion and does not load the bones and muscles in the same way as a specially designed workout. Too much physical labor could also increase the risk of exhaustion or injury. The crew would have to find a balance between moving enough and using their strength safely. Low gravity would also affect the heart and circulatory system. On Earth, the heart must continuously move blood from the lower body toward the brain against gravity's downward pull. Blood vessels contract and relax to regulate pressure whenever a person stands, sits, or changes position. In an environment with weaker gravity, that workload decreases, and the body begins adapting to the new demand. This adaptation would not necessarily be an illness while the person remained on Mars. The body would simply be adjusting to function more efficiently in its current environment. The problem would emerge when humans had to transition between different levels of gravity. They would experience microgravity during the journey, 0.38 g on the surface, and perhaps microgravity again before returning to Earth's full 1 g. Each transition forces the cardiovascular system to relearn how to keep blood flowing to the brain and maintain stable blood pressure. A person who feels healthy on Mars may still become dizzy or faint when returning to an environment with a stronger gravitational pull. Their tolerance will depend on how long they have lived there, how consistently they have trained, and the individual characteristics of their body. Health, therefore, cannot be judged solely by someone's ability to work normally inside the base. During the journey, bodily fluids tend to shift upward because gravity is no longer pulling them toward the legs. The face may appear fuller, while the legs become thinner as fluid volume decreases. This change affects more than appearance. It is also connected to pressure around the head, the eyes, and the blood vessels. After spending long periods in space, some astronauts develop changes in the shape of the eye and the optic nerve. Once they reach Mars, gravity will pull fluids downward more strongly than it did in orbit. This may help the body return to a condition closer to what it experiences on Earth, but it remains unclear whether 0.38 g is enough to fully reverse changes that have already developed. The eyes may recover partially, remain unchanged, or continue changing in a different way. The answer is especially important because vision is essential for nearly every repair and medical task. Eyesight must be monitored throughout the mission. Eye examination equipment needs to be compact enough for use inside the base, and the crew must know how to capture images and recognize changes that may be concerning. Guidance from Earth can help, but communication delays make local assessment essential. A slowly progressing vision problem may not create immediate danger, yet it could have serious consequences during a mission lasting many years. The inner ear also needs time to understand the new environment. The vestibular system uses motion and gravity to help the brain determine direction, speed, and body position. In microgravity, those familiar signals no longer resemble what the body experiences on Earth. After landing, gravity returns, but at a much weaker level, forcing the brain to develop a new way of interpreting it. The eyes may see the floor below, while the inner ear does not necessarily provide a sensation that fully agrees with that view. The result may be dizziness, inaccurate steps, or the feeling that the body is tilted even while standing upright. These symptoms usually diminish as the brain adapts, but the first few days must still be treated as a period of elevated risk. Astronauts should not immediately perform tasks requiring precise balance before they have been evaluated. A stumble on Mars may be more serious than it first appears. The surface contains rocks, small depressions, cables, and equipment placed around the base. The suit makes the body bulky, while the gloves limit a person's ability to catch themselves during a fall. Striking a sharp edge could injure the astronaut or damage the protective layer that maintains pressure. Movement must therefore be learned again. Astronauts need to understand how long each step should be, how quickly to turn, and how to stop a moving object. Pre-flight training can reproduce some of these conditions, but it cannot fully recreate the sensation of landing after many months in microgravity. The first days on the surface are both working time and a period in which the body must be trained all over again. Nutrition becomes an important tool for supporting bones and muscles. The body needs enough protein, calcium, vitamin D, and energy to maintain tissue and recover after exercise. If food intake is insufficient or an astronaut loses their appetite, the effectiveness of the training program will decline. The body cannot rebuild what it has not been given the materials to create. Food for a Mars mission may need to remain in storage for a very long time. Over several years, some vitamins degrade, while flavor and texture may also change. Radiation, stress, and a demanding work schedule could make nutritional requirements more complicated than expected. Eating enough depends not only on how much food is stored, but also on whether the body can tolerate the same meals being repeated again and again. Certain medications that help preserve bone may be considered, but they cannot completely replace mechanical loading. Drugs also have side effects, expiration dates, and varying effects from one person to another. Their use must be guided by health monitoring rather than treated as a universal solution for every astronaut. Exercise, nutrition, medication, and medical observation must support one another instead of relying on a single measure. Artificial gravity is sometimes considered a more direct way to protect the body during the journey. If the spacecraft, or part of it, rotates, that motion can push the body outward and create a sensation similar to gravity. A small centrifuge could also place the user under load for a limited period. This idea has been studied for many years, but it has not yet become a standard system aboard crewed spacecraft. A small centrifuge creates a large difference between the force experienced at the head and at the feet, and it may cause dizziness when the user turns their head. A larger structure would provide a more comfortable experience, but it would increase the spacecraft's mass, size, and complexity. The rotating system would have to remain balanced, be maintained, and operate safely throughout the journey. Creating gravity with machinery introduces yet another system the crew must keep running. On the surface, small rotating facilities might be built to provide higher gravitational loading for part of each day. People living on Mars for many years could use them as a form of therapy or specialized exercise. However, there is not yet enough evidence to determine the necessary duration, force level, or frequency. Spending 1 hour near 1G each day may be helpful, but no one can yet say whether it would be enough to protect health over an entire lifetime. The question of returning to Earth therefore has no simple answer. It would be wrong to conclude that everyone who lives on Mars for a long time will become permanently exiled there. The ability to return would depend on the duration of residence, age, degree of physical decline, training program, and available medical support. The human body is capable of adaptation, but the extent of that adaptation will differ from one person to another. The return journey could still be extremely demanding. After leaving the surface, the body would spend many more months in microgravity before enduring the acceleration of re-entry and the full pull of Earth's gravity. Muscles that were strong enough to function on Mars may not yet be ready to support the body's entire weight on Earth. The heart and blood vessels would also need to adjust quickly as gravity pulls blood toward the legs with much greater force. After landing, returning astronauts may need assistance standing, moving, and recovering. This does not mean they have permanently lost the ability to live on Earth. Recovery may take place gradually through physical therapy, nutrition, and medical monitoring. However, the longer a person remains on Mars, the greater the uncertainty becomes. The most important gap in our knowledge is that no human has ever lived for an extended period in a gravitational environment between microgravity and 1G. Animal studies, computer models, and simulation devices provide only clues. They cannot fully reproduce an adult human body living, working, and aging under Martian gravity. Every long-term plan must acknowledge that limitation. A gravity level of 0.38 G certainly provides more mechanical loading than an environment of near weightlessness. But being better than microgravity does not mean it is enough to maintain lifelong health. Bones and muscles may preserve most of their function, or subtle changes may accumulate over many years and become apparent only after they are too advanced to reverse completely. No one today can say with certainty which outcome will occur. The first people to live on Mars will therefore be more than astronauts. They will also, unintentionally, become the first source of data on the human body under partial gravity. Every change in bone, muscle, heart function, vision, and balance will need to be monitored over the long term. That information will shape habitat design, exercise programs, and mission duration for those who arrive later. A single step onto the surface will also begin a biological experiment unlike any before it. The body can be supported through exercise, nutrition, medication, and devices that provide additional loading. Yet all of these measures exist only while the base still has electricity to power exercise equipment, water to sustain the body, air to breathe, and temperatures stable enough for people to recover. A living body cannot be protected separately from the artificial environment surrounding it. When the astronaut goes to sleep, their bones and muscles continue adjusting to the planet's gravitational pull. Behind the walls, however, Fans must also keep turning. Pumps must keep water circulating, and sensors must ensure that the mixture of gases remains safe. The biological machine inside each person can adapt only if the larger machine surrounding them never stops working. The base is no longer simply a shelter from wind, dust, and radiation. It must perform the work of an entire atmosphere by maintaining pressure, producing oxygen, removing waste gases, and detecting changes before the human body can sense them. Even after everyone has fallen asleep, the habitat must continue to breathe. Once the astronauts have fallen asleep, the base seems to grow quiet. The lights in the living quarters dim, the displays shift into night mode, and nearly all movement disappears. Yet, behind the walls, fans continue to turn. Pumps keep pushing fluids through pipes, and air flows steadily through the filters. This house cannot sleep alongside the people living inside it. Every breath removes a small amount of oxygen and returns carbon dioxide and water vapor. These changes are too slight to notice inside a room on Earth, where outside air can always enter through doors, small gaps, or ventilation systems. On Mars, the base is almost completely isolated from the environment beyond its walls. Everything that is exhaled remains inside until machinery processes it. The habitat therefore functions almost like an artificial organism. Air filters perform the work of lungs. The water network resembles a system of blood vessels. The power supply acts as the heart, and waste processors carry out part of the work of the kidneys. Sensors spread throughout the base form something like a nervous system, continuously checking pressure, temperature, humidity, and air composition. If one component weakens, others must carry a greater load, or the entire level of activity must be reduced. No system can be allowed to stop for long. A failed fan may prevent the air from mixing evenly, a stalled pump may allow heat to build up inside equipment, and a declining filter may let waste gases rise hour by hour. A malfunction does not necessarily make the base uninhabitable at once. More often, it begins by slowly reducing the amount of safe time the crew has left. Pressure inside the base is far higher than in the Martian environment outside. The trapped gas constantly pushes against the walls, doors, and joints, as though the habitat were a large pressurized vessel. Every square inch of its shell must resist the continuous force, trying to drive the air outward. The walls do more than keep out cold and dust. They prevent the entire living environment from dispersing into the thin atmosphere surrounding the planet. A well-designed habitat should not consist of one large, undivided space. Sleeping quarters, work areas, medical rooms, and technical compartments must be capable of being sealed separately. If a leak develops in one section, the crew can isolate it and continue living in the remaining modules. A sealed door closed at the right moment may prevent them from abandoning the entire base because of one small opening. A large puncture usually creates obvious signs. Pressure falls rapidly, escaping air produces a sound, and the alarm system may identify the affected area. A very small leak is much harder to detect. It may cause only a gradual pressure loss that closely resembles normal changes produced by temperature, airlock operations, or the number of people occupying each compartment. Sensors must distinguish between these ordinary variations and genuine air loss. The crew may monitor pressure in each section and use sensitive microphones, ultrasonic instruments, or tracer gases to locate the leak. Within a network of pipes, valves, and connections extending throughout the base, identifying the exact location may take many hours. During all that time, the reserve supply of gas continues to decline. Repairing the damage is not simply a matter of sealing a hole and returning to normal life. The surrounding material must be inspected for cracks, fatigue, or trapped dust. A gap appearing in one seal may indicate that other seals of the same type are also beginning to deteriorate. Every failure becomes an opportunity to understand how the entire system has changed after months of operation on Mars. Even without a leak, humans continuously alter the air around them. Oxygen is absorbed through the lungs, while carbon dioxide returns to the cabin with every breath. If it is not removed, this gas may accumulate until it causes headaches, fatigue, reduced concentration, and eventually more serious danger. The crew may begin suffering from rising carbon dioxide long before the oxygen supply is truly depleted. The system must therefore do more than produce additional oxygen. It must also remove waste gas from circulation without interruption. Absorbent materials can capture carbon dioxide and later be regenerated for reuse. Disposable chemical scrubber cartridges may be stored for emergencies. If the primary system fails, the crew may move into a smaller compartment, reducing the volume of air that must be processed and extending the time available for repairs. The air must also remain evenly mixed. In a sealed environment, the average reading across the entire habitat may remain safe while carbon dioxide begins accumulating in one small area. Weak airflow near a bed, a workstation, or behind a large piece of equipment can create pockets of air with a different composition. A small fan that stops turning may therefore matter far more than its simple appearance suggests. The crew cannot rely only on discomfort to recognize a problem. The body may temporarily adapt, or symptoms may develop too slowly to reveal their exact cause. Sensors must monitor both average levels and changes within individual areas. In a long-term habitat, airflow must be designed as carefully as emergency exits or electrical networks. Fresh oxygen can be produced through the electrolysis of water, using a principle similar to the one employed aboard the International Space Station. Electricity separates water molecules into oxygen and hydrogen. The oxygen is released into the air for the crew to breathe, while the hydrogen can be processed further or used in other reactions. This process turns water and electricity into two direct requirements of every breath. That connection also creates dependence. If electrical power declines, oxygen production may have to slow as well. If water becomes scarce or the water treatment system fails, the supply available for electrolysis is also affected. The atmosphere inside the habitat does not exist as an independent system. It is tightly connected to water, energy, and the ability to maintain machinery. Another possibility is to use the Martian atmosphere itself. The MOXIE instrument aboard the Perseverance rover demonstrated that carbon dioxide from the planet's atmosphere could be collected and converted into oxygen. Across 16 operating runs, MOXIE produced a total of 122 grams of oxygen, reaching a maximum rate of about 12 grams per hour at a purity of at least 98%. This was important evidence that the gas outside could be transformed into a useful resource. Yet 122 grams of oxygen is still an extremely small amount compared with the needs of a crewed base. MOXIE was designed to prove the principle, not to sustain human life continuously. A practical system would have to be far larger, operate reliably through dust, cold, and changing temperatures, and diagnose its own condition without an engineer constantly standing beside it. The oxygen would also have to be compressed, stored, and safely distributed wherever it was needed. The greatest demand might not even come from breathing. Rocket engines require far more oxidizer than the crew would consume as breathable oxygen. If the propellant for the return journey were produced on Mars, the system would need to operate for months or years before the astronauts arrived. The stored supply would have to reach a predetermined level rather than waiting until the crew landed before production began. This would turn a solitary machine operating on the surface into a deciding factor in whether humans should leave Earth at all. If the oxygen and return propellant had not been confirmed, the entire mission would depend on a system whose ability to function over the long term remained unproven. A safer plan would require backup sources or a reserve large enough to prevent the return journey from relying on a single machine. Inside the living quarters, carbon dioxide must still be processed every minute. When a filter begins losing efficiency, the system may increase fan speed or redirect airflow through another device. The crew may also reduce physical activity and gather within fewer compartments to temporarily lower the demand. These measures do not solve the underlying problem, but they extend the time available before the environment becomes dangerous. Redundancy does not simply mean placing two identical machines beside one another. If both share the same design flaw, are affected by the same dust, or rely on the same vulnerable component, they may fail at nearly the same time. A safer system needs multiple ways of performing the same essential task. The primary scrubber may be regenerable for long-term use, while simple chemical absorption cartridges remain available for emergencies. This backup method may be less efficient than the main system, but it could be easier to operate and less dependent on electricity. During a prolonged repair, the goal is not to keep the base in its most comfortable state, but to hold the environment within limits, the human body can tolerate. Temperatures may be allowed to fall, work schedules may be canceled, and the crew may have to live in a smaller space. Comfort would be sacrificed in exchange for more time. Along with oxygen and carbon dioxide, humidity must also be controlled continuously. Breathing, perspiration, cooking, and growing plants all release water into the air. If humidity becomes too low, the eyes, skin, and airways may dry out, causing discomfort and increasing the risk of irritation. If it rises too high, water begins condensing on cold surfaces and creates conditions in which fungi and other microorganisms can grow. Condensation does not always appear where it can easily be seen. It may form behind a wall panel, around a cold pipe, or within insulation. A small damp area may remain hidden for weeks, becoming a place where microorganisms grow without the crew knowing. By the time an unfamiliar odor appears, the source may already have spread across several surfaces and filters. Humidity control is therefore also part of the water and sanitation systems. Water vapor is collected, deliberately condensed, and returned to the treatment network. A droplet that leaves the body through breathing or perspiration is not discarded, but begins a new journey. Inside a sealed habitat, even moisture suspended in the air becomes a resource that must be recovered. Air quality is also affected by many other compounds. Plastics, adhesives, paint, cleaning products, electrical wiring, electronic equipment, and cooking can all release tiny quantities of gases. On Earth, these substances are often diluted within a much larger environment or allowed to escape outdoors. Inside a Martian habitat, they may accumulate over months unless the filters are specifically designed to remove them. The human body also produces odors and many compounds through the skin, breath, and metabolic activity. A small group living in a sealed environment will continuously release these substances into the same volume of air being reused again and again. The filtration system, therefore, cannot focus only on oxygen and carbon dioxide. It must also remove many compounds present at low concentrations that may become unpleasant or harmful when allowed to accumulate over long periods. Sensors cannot perfectly measure every substance present inside the cabin. When an unfamiliar odor appears or a reading begins to change, the crew must search for the source by isolating individual devices, inspecting filters, and comparing data from different compartments. A piece of material that has overheated or a cleaning product used in the wrong amount may be enough to cause the problem. Keeping the air clean depends on both machinery and disciplined daily routines. One of the greatest dangers in an environment filled with electrical equipment is fire. The base needs oxygen to keep humans alive, but that same oxygen also allows flames to continue burning. Smoke and toxic gases cannot be released simply by opening a window, while evacuating outside requires spacesuits, an airlock, and time to prepare. Even a small fire inside an electrical panel could make an entire living area unusable. Materials inside the habitat must be difficult to ignite and produce as little toxic smoke as possible. Sensors need to detect heat or combustion products before flames have time to spread. Fire extinguishers must be suited to a sealed environment and must not release large amounts of additional toxins into the air. Even after the flames are extinguished, all the air in the affected area must still be filtered before people can safely return. Once again, the ability to seal individual compartments becomes essential. If a fire begins in a technical section, the crew may isolate that area and prevent smoke from spreading into the sleeping quarters or medical bay. Closing the doors, however, also means losing access to the equipment inside. A section spared from the flames may still remain unusable until its pressure, toxic gases, and electrical systems have been fully inspected. The atmosphere inside the base does not necessarily have to match the exact conditions found at sea level on Earth. Engineers may choose a lower pressure to reduce stress on the structure or shorten the preparation time required before going outside. The oxygen concentration could then be adjusted so that the body still receives enough. But changing one factor always introduces other risks. A mixture with a higher proportion of oxygen makes materials more likely to burn. Lower pressure may affect health, sleep, and work performance if the design is not carefully managed. The difference between cabin pressure and suit pressure also determines how long astronauts must prepare before each excursion. No single option is perfect for every goal, so the design must balance fire safety, human health, structural demands, and daily operations. Plants could support part of the atmospheric cycle. They absorb carbon dioxide, release oxygen through photosynthesis, provide fresh food, and offer a sense of closeness to living nature. Inside a sealed base, a few green leaves may have a psychological value far greater than their size would suggest. Yet a small greenhouse cannot replace the entire life support system. Plants also respire, especially when there is no light, and they require water, nutrients, suitable temperatures, and protection from disease. If the lighting or irrigation system fails, they may consume resources without providing enough benefit in return. A failed crop could also change the levels of water vapor, carbon dioxide, and organic matter inside the habitat. Biology is not automatically simpler than machinery. During the earliest missions, crops would be better suited to a supporting role. They could provide fresh food, improve morale, and contribute to part of the air cycle, while engineered systems continued to carry the primary responsibility. As cultivation expands, the dependence between the greenhouse and the living quarters would also grow. A small ecosystem must be built gradually. Air filters cannot simply be replaced by adding more plants to a room. As the night passes, the base continues adjusting itself without interruption. A fan speeds up as carbon dioxide levels begin to rise. A condenser collects additional water vapor, and the electrolysis system prepares to produce a fresh supply of oxygen. No one in the sleeping quarters needs to wake up and perform each of these actions. Life is sustained by thousands of small responses happening at exactly the right time. Yet, this cycle is not completely closed. Oxygen can be regenerated as long as water and electricity remain available, and moisture can be recovered as long as the pumps and filters continue working. Every process involves some degree of loss, and stored supplies cannot last forever unless they are replenished. Behind every renewed breath is a drop of water that has already traveled through many pipes. By morning, an astronaut lifts a cup of water without seeing the journey behind it. Some of that water may once have been breath, perspiration, or fluid recovered the previous day. After entering the body, it will eventually leave again and return to the treatment system. On Mars, no drop of water can be allowed to serve only once. Morning inside the base begins with a glass of water. An astronaut drinks slowly, sets the glass down, and continues working as though the water has completed its purpose. But on Mars, a drop of water cannot be used only once. After entering the body, it will become part of the breath, perspiration, urine, and waste, then must be collected, purified, and returned to circulation. On Earth, this process unfolds across the scale of an entire planet. Sunlight causes water to evaporate from the oceans, moisture gathers into clouds, and rain falls onto the land before flowing through rivers, lakes, and underground aquifers. The atmosphere, rocks, soil, microorganisms, and plants all help purify and distribute it. Inside a Martian base, that enormous cycle must be reduced to pumps, filters, membranes, catalysts, pipes, and storage tanks, separated by only a few yards. There is no river outside to replenish the tanks when they run low, nor will rain appear if the treatment system fails. Every stage of water's journey must be designed in advance, from the moment moisture is removed from the air until clean water returns to the drinking tap. A single stuck valve or declining filter can begin to slow the entire cycle. The most practical lessons available today come from the International Space Station. There, water is recovered from cabin humidity, breath, perspiration, and astronaut urine. The untreated water passes through several processing stages to remove impurities, microorganisms, and unwanted compounds before being used again. After equipment was added to process the concentrated brine, the overall system became capable of recovering nearly 98% of the water. This is a remarkable achievement, but 98% is still not a completely closed cycle. If 100 parts of water enter the system, roughly 2 parts are still lost and must be replaced. Over a few weeks, that loss may not seem significant, but during a mission lasting many years, the water disappearing across thousands of cycles would add up to an amount large enough to affect survival. Water also remains trapped in food, used filters, cleaning materials, and portions of waste that cannot be fully recycled. Small amounts may remain inside pipes, insulation, or equipment that has been removed from service. No major failure has occurred, yet the total reserve continues to decline little by little. Efficient recycling can greatly reduce the amount of water transported from Earth, but it cannot eliminate the need for a local source of replenishment. Fortunately, Mars is not entirely dry. Data from orbiters and radar instruments indicates that water ice exists beneath the surface in many regions. Some areas may contain ice relatively close to the ground, particularly at colder latitudes. The SWIM project combined data from multiple missions to identify locations where ice may be accessible, while still remaining near regions more favorable for landing and habitation. A marked location on a map, however, does not guarantee that a drill will encounter a clean layer of ice. The ice may exist in small deposits, be mixed with soil and salts, or lie deeper than expected. Its thickness and purity may change over even a short distance. A site containing abundant but widely dispersed ice could require more energy than one with a smaller amount concentrated in a clearly defined layer. For this reason, access to water may influence the location of the base more strongly than scenery or scientific value. The habitat must be close enough to the ice to limit transportation distances, but it cannot be placed somewhere too cold, too steep, or too difficult for a lander to reach. Regions near the equator receive more sunlight and are warmer, while areas with more accessible ice are generally colder. No location satisfies every requirement perfectly. A suitable site must balance sunlight, temperature, elevation, terrain, radiation, communication, access, and the resources beneath the ground. Building near ice may cause heating systems to consume more electricity. Choosing a sunnier location may require robots to transport water across much greater distances. Every decision reduces one difficulty, while usually placing additional pressure on another system. Once the ice has been located, humans still need to bring it into the base. One option is to excavate ice-bearing material and transfer it into a sealed chamber. Heat would cause the ice to become vapor, which could then be collected and condensed inside a separate tank. The remaining soil would be removed, while the untreated water continued through the purification process. Another method would send heat directly beneath the surface and collect the resulting water vapor without excavating as much soil. This could reduce the number of moving parts exposed to dust, but it would require extremely precise control of heat and vapor flow. If the vapor migrated through the ground instead of entering the collection system, the energy would be wasted. The true efficiency would also depend on the geological structure at each location. Whichever method is used, extracting water would require a significant amount of electricity. Excavators, heaters, pumps, and condensers would have to operate in an environment that is cold, dusty, and exposed to large temperature swings. A layer of ice lying just beneath the surface is still not a ready supply of usable water. It becomes a resource only when an entire chain of machinery can extract it, purify it, and deliver it to a storage tank. The newly extracted water could not be consumed immediately. The ice might be mixed with dust, salts, minerals, and perchlorates from the Martian material. It would need to be filtered, stripped of unwanted ions, tested for chemical composition, and disinfected before entering the living system. In a closed environment, even a substance present at a low concentration can accumulate as the water passes through repeated cycles. Perchlorates are among the substances that would require careful monitoring. These salts have been detected in Martian surface material and may affect human health if they enter the body in sufficient amounts. They also complicate the use of soil and water for growing plants. The treatment system must reduce their concentration to a safe level rather than merely making the water clear and odorless. A failure in the treatment system might not cause the water to disappear, but it could make the entire contents of a tank untrustworthy. Until testing is complete, the crew may have to stop using hundreds of liters, even though the liquid remains directly in front of them. On Mars, water quality matters just as much as quantity. A full tank of unsafe water is almost the same as an empty one. The base therefore needs several separate storage tanks rather than relying on one large reservoir. Drinking water, technical water, untreated water, and emergency reserves must be clearly divided. If one tank develops a leak or becomes contaminated, the others can still support basic needs. A valve in the wrong position must never be allowed to send wastewater back into the clean supply line. These tanks could also be arranged around the radiation shelter. Because water contains a great deal of hydrogen, it can help reduce the effects of certain high-energy particles. When positioned carefully, the same resource can provide drinking water while adding another layer of protection around the crew. This design, however, would also require a flexible network of pipes, so that repairing one tank would not remove both the water supply and the shielding it provides. Water is also directly connected to the air. During electrolysis, water molecules are separated into oxygen and hydrogen. The oxygen can be released into the cabin for the crew to breathe or stored for other needs. In some fuel production designs, the hydrogen can then react with carbon dioxide to create methane, turning the water supply into part of the plan for leaving Mars. This means that every kilogram of water must be allocated with great care. Water being used to produce fuel is no longer available in the drinking tanks at that moment. Water assigned to crops cannot simultaneously serve as an emergency medical reserve. Under normal conditions, computers may balance these demands. But when extraction declines, the base must decide which systems will receive priority. If the excavator operates more slowly than expected, fuel production may have to be postponed. If one tank becomes contaminated, the amount of water allocated to the greenhouse may need to be reduced. Choices like these protect immediate needs but leave consequences for the future. Crops grow more slowly, fuel reserves fall behind schedule, and emergency margins become increasingly thin. Water also determines how people eat. The earliest missions may rely largely on packaged food from Earth because it is compact, easy to control, and provides a relatively precise amount of energy. However, a Mars mission may require food to maintain its quality for many years, especially when supplies are sent in advance and must also cover unexpected delays. Over long periods, some nutrients decline even when the packaging remains intact. Studies of space food have shown that vitamin B1 and vitamin C are among those most likely to diminish during storage. A meal may still be safe to eat while no longer providing the same amount of vitamins it contained when it was first produced. Shelf life, therefore, is not only about spoilage, but also about how much nutritional value remains. Food for a Mars mission may need to preserve its quality for roughly 5 years. That period includes the time spent waiting after being sent ahead, the journey through space, the stay on the surface, and additional reserves in case the return schedule changes. This is far more demanding than preparing meals for an orbital mission lasting only a few months. Flavor, texture, and vitamin content must all be considered. One possible solution is to produce certain nutrients when they are needed rather than carrying the entire supply from Earth. The Bionutrients Project studies ways to store microorganisms in a stable form and later activate them with water to produce vitamins or other useful compounds. Yeast spores may remain dormant for long periods and begin functioning once the right conditions are provided. This technology does not turn a small package into a complete meal. It is more like a miniature biological factory designed to produce compounds that gradually decline in stored food. The microorganisms require clean water, suitable temperatures, and testing procedures to ensure that the final product is safe. A biological solution may reduce the amount of cargo carried from Earth, but it still depends on equipment and human supervision. Crops could provide fresh food and reduce the monotony of packaged meals. Leafy vegetables offer flavor, color, and certain vitamins that are difficult to preserve for years. The scent of leaves, the humidity of the growing area, and the sight of plants slowly developing may also create a sense of closeness to living nature. Inside a base made mostly of metal, plastic, and screens, the growing chamber could become a place where people recover a small part of Earth. Plants, however, do not produce food for free. They need water, light, nutrients, space, and time for care. If the lights operate at reduced power because energy is limited, growth will slow. If an irrigation pump becomes clogged or fungi spread through the growing area, an entire crop may fail long before assistance from Earth could arrive. Martian soil is not something that can simply be placed into a pot. The surface material lacks the organic matter and complex microbial communities commonly found in fertile soil on Earth. It may also contain salts and perchlorates that are unsuitable for crops. Before it could be used, the material would need to be treated, washed to remove harmful components, and supplemented with what it lacks. During the early years, crops would be more likely to grow through hydroponics, aeroponics, or specially prepared substrates. Hydroponic systems place roots in a nutrient-rich water solution, while aeroponic systems spray a fine mist directly around them. Both methods allow more precise control over water use and avoid bringing large quantities of Martian dust into the living area. In return, these growing systems depend on pumps, sensors, and pipes. If the nutrient solution stops circulating, roots may lose oxygen or dry out very quickly. A small imbalance in nutrient concentration lasting several days may weaken the plants before the crew notices any visible change in the leaves. A water-efficient system remains effective only while its control equipment continues to function correctly. The choice of crops cannot be based on yield alone. Growth time, edible proportion, height, water consumption, and the amount of waste produced must all be considered. A plant that creates large quantities of inedible stems and leaves may increase the burden on waste processing systems. Fast-growing varieties with a high edible fraction are often more useful, but the diet must also remain varied enough to prevent monotony. Some species would need to be pollinated by hand or with controlled airflow. Insects might assist in the future, but they would require their own habitat and careful management. Light cycles, temperature, humidity, and carbon dioxide levels must be adjusted for each species. A greenhouse, then, is not merely a room filled with lamps, but a living environment that must be continuously controlled. Once food has been consumed, what remains still contains valuable resources. Organic waste holds water, carbon, nitrogen, and minerals that crops may need. A long-term base cannot continue sealing everything in bags and placing it in storage forever. Unless part of that material is returned to circulation, fertilizer and nutrients will gradually become piles of waste with no remaining use. The recycling process must remove pathogens and prevent chemicals from accumulating. Human waste cannot be transferred directly into the growing area because it may contain disease-causing microorganisms, medications, and many other compounds. If treatment is incomplete, these substances could pass into plants and return through the food supply. A closed cycle can also trap its own mistakes, allowing harmful materials to become more concentrated with every round. Microorganisms may help break down organic matter and convert some of it into forms that plants can absorb. But the microbial system also requires the right temperature, moisture, and chemical balance. If the necessary populations decline, processing will slow. If an unwanted species grows too aggressively, the final product may no longer be safe to use. Even when every calculation is correct, a meal is more than energy and vitamins. Eating marks the passage of the day, gives the crew a chance to sit together, and preserves familiar routines. A dish that tastes almost like something from home may bring back memories of family, a city, or an evening beneath a blue sky. In an isolated environment, that psychological value is difficult to measure with numbers. Months of repeated packaged meals may gradually reduce appetite. Someone who is tired or under stress may eat less even while the body still needs energy. If the menu meets every requirement on paper but does not make people want to eat, the nutritional plan may still fail. Flavor, color, and variety become part of preventive medicine. Cooking a warm meal can also make the base feel like a home rather than merely a laboratory. But cooking uses electricity and produces heat, moisture, odors, and waste. Every meal becomes part of the air and water cycles. Even the most ordinary moment remains connected to the systems operating behind the walls. The morning glass of water may once have been part of another person's breath. It may have passed through filters, rested inside a storage tank, and then traveled to the kitchen. After entering the body, it begins another cycle. On Mars, water does not truly belong to one person or serve only one purpose. It moves continuously among breathable air, food, hygiene, crops, and fuel. Yet no cycle moves by itself. Pumps need electricity to push water through membranes, Heaters need electricity to draw vapor from the soil, and lamps need electricity to nourish plants. Refrigeration equipment keeps food stable, while electrolysis systems use water to produce oxygen. Water may be the bloodstream of the base, but electricity is the force that keeps it flowing. If the power supply weakens, the base does not simply become darker. Ice extraction slows, the supply of replacement water declines, and the greenhouse receives less light. Electrolysis produces less oxygen, refrigeration systems must conserve energy, and fuel production is delayed. The entire habitat does not stop at once, but each of its cycles begins to slow. By the end of the day, the glass has long been empty, yet the water it once contained is still moving through bodies, pipes, and filters. No drop can be allowed to stray too far from the cycle, because every loss makes the remaining reserves smaller. But for water to keep returning, an entire network of machines must still have enough energy to operate. On Mars, electricity does more than turn on lights or power computers. It keeps air circulating, water clean, and crops growing. When the electrical pulse begins to weaken, the base does not die immediately. It simply starts to slow down, like a body whose heart is gradually failing. The problem begins with a small number on the control screen. Power output from the solar array is lower than expected. Not enough to trigger an alarm, but enough for the computer to recalculate the base's entire energy plan for the day. A list immediately appears, showing which systems can operate at reduced power: the greenhouse lights, the ice extraction equipment, the repair workshop, the scientific instruments, and the system producing fuel for the return journey. None of the equipment on that list is truly unimportant. Turning down the greenhouse lights will slow plant growth, stopping ice extraction will prevent the water reserves from being replenished, and delaying fuel production may affect the departure schedule many months later. The crew is not choosing between what is essential and what is useless. They must decide which need can wait the longest without creating another problem. On Earth, a power outage is usually noticed first through darkness, a stopped air conditioner, or a device that can no longer be charged. Inside a Martian base, lighting is only a small part of the network. Electricity keeps ventilation fans running, produces oxygen, purifies water, provides heat, refrigerates food, maintains communications, and powers medical equipment. It also supplies energy to robots, vehicles, computers, and every sensor monitoring the living environment. Air, water, and food may already be present inside the base, but most of them are usable only while electricity remains available. Contaminated water must be pumped through filtration membranes, underground ice must be heated, and carbon dioxide must be moved through absorption systems. Electricity does not create every resource from nothing, but it transforms those resources into forms the human body can use. It is therefore not merely a convenience, but the condition that allows every other system to remain alive. The most visible source of energy is sunlight. Mars orbits the Sun at an average distance about 1.52 times greater than Earth's, so each square meter there receives only about 43% of the solar energy available to the same area near Earth's orbit. Solar panels can still work effectively, as many robotic missions have demonstrated, but a base would need a much larger surface area to generate the same amount of power. Output would also vary with latitude, season, the angle of incoming sunlight, and the sun's position in the sky. Panels near the equator may experience more favorable conditions during much of the year, while regions closer to the poles face long winters and lower solar angles. Even on a clear day, power rises gradually after sunrise, reaches its highest level around midday, and declines again as the sun sinks toward the horizon. Temperature also affects the performance of the panels and the storage system. Photovoltaic cells may operate more efficiently when they are not too warm, but electronics and chemical batteries must remain within suitable temperature ranges. During the night, extreme cold can reduce battery performance or cause damage if the units are not heated. Some of the electricity produced during the day must therefore be used simply to protect the power system itself. Dust makes the equation even less predictable. Even without a major storm, fine particles slowly settle on the panels and reduce the amount of light reaching the photovoltaic cells. A thin coating on one panel may appear insignificant, but when it spreads across thousands of square meters, the total loss of power may be enough to force the base to change its operating schedule. In the past, winds have occasionally cleared dust from the solar panels of certain rovers, causing their power levels to rise unexpectedly. But a crewed base cannot build its survival plan around unpredictable natural cleaning events. Dust removal robots, vibration systems, non-stick coatings, and electrostatic forces may all help keep the surfaces cleaner. Yet every solution requires its own motors, sensors, wiring, and software. The cleaning equipment also consumes the very electricity it is trying to protect. If the dust becomes too thick, the robots must operate longer, but by then power production has already declined and the available energy has become limited. The crew may have to send people outside to clean the panels manually, consuming oxygen and time while increasing their exposure to radiation. A very thin layer of dust can create a chain of costs that is anything but small. Regional or global dust storms present an even greater challenge. Suspended particles darken the sky and reduce the sunlight reaching the surface for many days, sometimes longer. This does not mean that every solar panel immediately stops producing power altogether. The extent of the decline depends on the thickness of the dust, the location of the base, the season, and the design of the system. In 2018, a global dust storm sharply reduced the sunlight reaching the Opportunity rover. The rover entered a low-power mode, later lost communication, and was never recovered. Opportunity had already operated far beyond its original design life, so the event did not prove that solar power cannot be used on Mars. It simply showed that a system relying entirely on sunlight may face serious danger when the sky changes. A crewed base would need enough stored energy to survive the night and periods of reduced production. Chemical batteries could collect power when sunlight is strong and return it after sunset. However, the number of batteries required increases rapidly if they must sustain the entire base for several days. Ventilation, heating, atmospheric control, and communications cannot simply stop and wait for the sky to brighten. Batteries also do not preserve their original storage capacity forever. Every charging and discharging cycle changes the materials inside them slightly, causing their capacity to decline over time. Extreme cold, excessive heat, and radiation can make this aging process even more complicated. A battery bank that once provided 10 hours of operation may supply only 8 or 9 hours after several years. The system must therefore monitor each module rather than observing only the total capacity. A weak cell can make an entire battery string less stable, generate unusual heat, or prevent it from charging fully. If detected early, the affected module can be isolated and replaced. If ignored for too long, it may begin to affect much larger sections of the storage network. Carrying enough batteries for every possible situation is not a perfect solution either. Batteries are heavy, occupy valuable space, and must be kept within a suitable temperature range. Every kilogram of battery delivered to Mars is a kilogram that cannot be used for food, medicine, or other equipment. Engineers must balance a safe reserve against the practical limits of transportation. A power source that does not depend on sunlight could greatly reduce this pressure. Surface fission systems are being studied as a way to provide continuous electricity over long periods, regardless of night, day, or dust storms. NASA has previously pursued designs capable of generating at least about 40 kilowatts, initially for operations on the Moon and potentially later for Mars. That output is comparable to the electrical demand of a small group of homes on Earth. But the needs of a Martian base are very different, because many systems must run continuously. A fission reactor produces heat by splitting heavy atomic nuclei, then converts part of that heat into electricity. Nuclear fuel contains an extremely concentrated amount of energy, allowing a relatively compact system to operate for years without sunlight. This would be especially useful during dust storms, throughout the night, or in regions with long winters. However, surface fission power on Mars remains a technology that requires further development and testing. The reactor must be transported safely, deployed either autonomously or with minimal human assistance, and activated at a suitable distance from the base. It also requires shielding, thermal control, and the ability to shut down safely if a component fails. Nuclear reactions produce far more heat than can be converted into electricity. The remaining heat must be released through radiators. On Earth, power plants can use water and air for cooling, but the Martian atmosphere is too thin to carry heat away efficiently through ordinary convection. Blowing outside air across a hot device would not cool it nearly as effectively as it would on Earth. The base would need closed fluid loops to carry heat from machinery to radiator surfaces. There, the energy would be released into space as infrared radiation. These radiator panels must be large enough, kept relatively free of dust, and positioned where they will not endanger the crew. A failure in the cooling system could cause equipment to overheat, even while the environment outside the base remains bitterly cold. Excess heat can also be used for certain purposes before it is released. It may help warm the living quarters, heat water, or prevent equipment from freezing. But heat is useful only when it appears in the right place, at the right time, and at the appropriate level. If it cannot be controlled, the same energy source that once helped the base survive can become the reason its machinery begins to fail. The base will most likely avoid depending entirely on a single source of power. Solar arrays can provide large amounts of energy on favorable days, while fission systems maintain a stable baseline. Batteries and other storage systems can balance periods of high production against times when demand exceeds supply. This combination reduces the risk of losing all electrical power because of one failure. In return, the electrical network becomes more complex. Power from the solar panels, reactor, and storage systems must pass through conversion equipment before being distributed across the base. If a cable short circuits or a device draws an unusual amount of current, the faulty section must be isolated before it affects the rest of the habitat. No single failure can be allowed to cut power to the life support system. The computers managing electrical loads must continuously compare available power with actual demand. When production falls, equipment cannot simply be shut down in a random order. The highest priority systems include ventilation, atmospheric control, minimum heating, and emergency communications. As long as these systems remain operational, the crew still has time to assess the situation and make repairs. Water processing, medical care, food preservation, and control computers belong to the next level. They may operate at reduced power for a short time, but they cannot remain offline for long. The greenhouse, scientific research, and industrial production may be cut first, although every interruption carries consequences. Calling a system low priority does not mean it is unnecessary. It only means the effects of shutting it down will take longer to appear. When output from the solar array declines, the base first shuts down non-essential scientific equipment. Greenhouse lighting is reduced to a level the plants can tolerate briefly, while the surface water extraction system temporarily stops operating. These changes preserve enough power to keep ventilation, heating, and atmospheric processing running normally. No one is placed in immediate danger on the first day. After several days, however, the effects begin to spread. The water reserves remain sufficient, but they are no longer being replenished as planned. Crops grow more slowly under reduced lighting, while the electrolysis system must direct most of its oxygen toward the cabin instead of storing it for fuel production. The schedule for producing oxidizer for the return journey begins to slip, even though departure is still far in the future. Meanwhile, a pump in the cooling system begins to vibrate slightly. Sensors show that the bearing temperature is rising, though it has not yet exceeded its safe limit. If the pump continues running, the base maintains stable power and thermal control, but the component may fail completely. If it is shut down for repairs, baseline electrical output will fall at the very moment the solar array is underperforming. This is the kind of decision that often appears within a life-critical system. No option is completely safe. There are only different levels of risk. The crew must assess the remaining electrical reserves, the pump's expected service life, and the time required to dismantle it. They must also consider what will happen if a replacement part does not fit or if the repair takes longer than planned. It is impossible to carry a duplicate of every component. Transportation limits mean the spare parts inventory must be selected with great care. Equipment that is likely to fail, difficult to repair, or essential to survival needs more replacement options. Components that can be used across several systems are especially valuable because a single item may solve many different kinds of failure. Sometimes an inexpensive seal matters more than a costly scientific instrument, If it is the only component maintaining pressure inside an oxygen line or cooling loop, the absence of one in the correct size could disable the entire system. Value on Mars is not measured by the manufacturing cost on Earth, but by how difficult something is to replace after it fails. A 3D printer may reduce part of this dependence. It could produce handles, brackets, protective housings, tools, or simple sections of pipe from available materials. If a plastic component cracks, the crew may be able to load its design and manufacture a replacement inside the base. This would be a major improvement over waiting for the next shipment to arrive. But a printer cannot easily create everything. Precision sensors, computer chips, high-quality bearings, medicines, and many specialized materials require far more complicated processes. Even printing a simple part demands the correct raw material, electricity, and a machine operating reliably. Local manufacturing does not erase the network of dependencies. It merely moves them to another level. To produce a wider range of components independently, the base would need machine tools, measuring equipment, heat treatment furnaces, and supplies of purified materials. Every new machine would require its own spare parts, maintenance, and trained operators. Self-sufficiency does not emerge simply by delivering a printer to Mars. It requires an entire small industrial chain, built one stage at a time. Robots can reduce the amount of outdoor work humans must perform. They can inspect solar panels, excavate soil, transport materials, and examine pipelines before astronauts leave the habitat. This lowers radiation exposure, limits the amount of dust entering the living quarters, and conserves oxygen inside the suits. Robots can also work in places that are too cold or dangerous for people. Yet, robots are not workers that require no care. They contain motors, batteries, wheels, joints, and cameras that dust can gradually wear down. Wiring may crack after repeated temperature cycles, and software can develop faults. The crew must maintain the machines that help them maintain the base, creating another cycle of dependence between humans and robots. High-energy particles from space can also affect electronic equipment. When one passes through a memory chip, it may change the state of a data bit, turning a 0 into a 1 or the reverse. This is known as a single-event upset, and it does not necessarily cause permanent hardware damage. Even so, a small change in control data could lead to the wrong decision if it goes undetected. Computers used in space often include error correction, cross-checking, and multiple copies of critical data. A system may compare results from several processors and reject the value that does not match the others. Equipment also needs the ability to restart or switch to a backup unit when an irregularity is detected. Critical operations should never depend on a single computer. Software must be designed so that one fault cannot immediately spread across every system. The control networks for ventilation, power, and water need clear boundaries, along with limits that automated commands cannot exceed. If the computers encounter a problem, humans must be able to switch to manual control or a simpler operating mode. The system may then become less efficient, but it can still preserve life. An emergency mode does not need to maintain every comfort. It only has to keep the atmosphere within safe limits, protect the water supply, preserve minimum heat, and maintain communication. The crew may live inside only a few compartments, use less equipment, and suspend scientific work. A simple system that is easy to understand may sometimes be more reliable than an optimized system too complex to repair. To manage this, the people living inside the base must understand several fields at once. One crew member may specialize in electrical systems, another in mechanics, medicine, or biology, but their skills must overlap enough that no individual becomes a single point of dependence. If the electrical engineer is injured, the others must still know how to isolate a circuit, inspect the power source, and activate the backup system. No one can become a complete expert in every field, so technical documentation plays an essential role. Diagrams, repair videos, inspection procedures, and three-dimensional models of equipment must be stored inside the base. The data needs multiple copies and must remain accessible when the main network is offline. A manual stored only on a server on Earth will be useless if communication is interrupted. The instructions must also be clear enough to use under stress. Images showing valve locations, the order in which parts should be removed, and critical safety limits must be presented directly rather than buried within hundreds of pages of description. The crew may practice on models beforehand or use augmented reality to display instructions directly over the equipment. Technical knowledge becomes a kind of spare part with no physical mass, yet one the base cannot survive without. When the pump begins to vibrate, its data is sent back to Earth for engineers to analyze. They may compare the sound, temperature, and power consumption with previous tests. But the signal does not travel instantly. Depending on the positions of the two planets, a message may take many minutes to arrive, and the response requires the same amount of time to return. During that interval, the pump continues running or continues deteriorating. The crew cannot postpone every decision while waiting for specialists hundreds of millions of kilometers away. They must rely on the data already available, the documentation stored locally, and their own experience. Earth can offer advice, but the final responsibility remains inside the room on Mars. This becomes even more apparent when the problem is no longer contained within a machine. A component can be removed, measured, and replaced according to a procedure. The human body is not a device manufactured from a single identical blueprint, and symptoms do not always point toward one clear cause. When someone experiences severe pain, loses consciousness, or is injured outside the base, the delay before an answer arrives becomes far more difficult to endure. Electricity must still keep the medical equipment operating, maintain the lighting, and transmit data back to Earth. But between the question being sent and the guidance returning lies a silence that cannot be shortened. During that interval, the crew must diagnose the problem themselves, make their own choices, and accept responsibility for the outcome. On Mars, the nearest hospital is not only very far away, its answers will always arrive later than the events already unfolding. The pain begins at midnight. At first, the astronaut feels only some discomfort in the abdomen and assumes it may have been caused by the previous meal. But after an hour, the pain has not faded. Instead, it has become more distinct. It could be nothing more than digestive trouble, or it could be related to a kidney stone, appendicitis, or another condition that requires immediate treatment. On Earth, a patient can be taken to a hospital, receive blood tests and medical imaging, and be examined by several doctors in a single day. On Mars, there is no ambulance, emergency room, or specialist waiting at the end of the hallway. The entire hospital must already be inside the base, carried there in the form of equipment, medication, knowledge, and the decision-making abilities of the people present. A rescue spacecraft cannot be launched only a few hours after an emergency signal is received. Earth and Mars are constantly moving along different orbits, so favorable opportunities for traveling between them generally occur about every 26 months. Even if a spacecraft were already prepared, the journey would still take many months. A serious illness must therefore be treated where it occurs. The crew cannot place the patient in a vehicle and transfer responsibility to another hospital. If the pain becomes severe, they must determine the level of danger themselves, perform tests, monitor vital signs, and choose how to intervene. From that moment on, the base is no longer merely a home and a laboratory. It must become a clinic, an emergency room, and sometimes even an operating room. Earth can still provide support, but that support will always arrive later than the events unfolding on Mars. Depending on the positions of the two planets in their orbits, a signal may take roughly 4 to 24 minutes to travel in one direction. Sending a simple question and waiting for the answer may therefore require nearly 8 to 48 minutes in signal travel time alone. That does not include the time doctors need to review the data and prepare their guidance. A live video call like those used on Earth would therefore be impossible. The crew sends images, test results, and descriptions of symptoms, then continues treating the patient while waiting for a response. By the time medical advice arrives, the patient's condition may already have changed. The crew must respond independently to every new development rather than pausing to wait for each instruction. The distance becomes even more difficult when Mars passes close behind the Sun from Earth's perspective. During solar conjunction, interference from the region around the Sun can make direct communication less reliable and force missions to limit the commands they transmit. These periods may last for many days. The base knows when they are coming, but the human body cannot be asked to avoid illness, according to an astronomical schedule. Before every period of limited communication, the crew must inspect its medical supplies, equipment, and emergency procedures once again. Essential documentation must be stored inside the base, rather than depending on servers on Earth. Likely scenarios need to be practiced beforehand, so that everyone knows what to do if assistance is unavailable. This preparation cannot eliminate risk, but it reduces the number of decisions that must be made from nothing. One crew member may receive more advanced medical training than the others, but no single person can replace an entire hospital. Family physicians, surgeons, dentists, critical care specialists, and laboratory technicians are separate professions on Earth because each field requires years of training. On Mars, one person may have to perform part of the work of all of them. The medically trained crew member is also part of the mission and may become ill or injured like anyone else. If all medical capability is concentrated in one person, the base may lose its healthcare capacity at the exact moment that person can no longer work. Basic first aid, diagnostic equipment use, and treatment of common emergencies must therefore be distributed among several crew members. Medical equipment needs to be compact, durable, and useful for many purposes. An ultrasound machine fits these requirements because it can examine the heart, blood vessels, muscles, abdomen, and certain injuries without requiring a large imaging system. The operator places the probe against the body, while software or stored instructions help identify the correct position and angle. The images can then be sent to Earth for further evaluation by specialists. Ultrasound cannot answer every question, but it can provide a great deal of information with a relatively compact device. In a case of abdominal pain, the images may help examine certain organs, detect unusual fluid, or rule out several possible causes. Software may compare the results with data collected before the mission, but an algorithm can only provide support. It cannot fully replace clinical judgment. The base also needs the ability to test blood, urine, microorganisms, and certain biological markers. The equipment must require only small samples because too much blood cannot be drawn repeatedly during a long mission. Testing chemicals must also remain stable for many years, survive transportation, and continue functioning in an environment with higher radiation levels than Earth. Every test consumes supplies. The crew cannot perform an extensive panel whenever a minor symptom appears, yet they must not overlook signs of a serious illness. They have to decide which tests are likely to change the course of treatment and which can wait. A cartridge used today will no longer be available for an emergency several months later. For abdominal pain beginning at midnight, the medical officer may start by measuring body temperature, heart rate, blood pressure, and blood oxygen levels. This would be followed by a physical examination, ultrasound imaging, and several basic tests. The results would be compared with the patient's medical history to identify what has changed. Each step narrows the possibilities, but sometimes the evidence still does not produce a completely certain answer. Medication has limitations of its own. Every drug has a shelf life and may degrade more quickly after long exposure to unsuitable temperatures or radiation. A tablet that still looks perfectly normal may no longer contain the same amount of active ingredient it had when it left Earth. The medical supply must therefore be stored, monitored, and tested strategically rather than managed only by the expiration date printed on the package. The base cannot carry large quantities of every possible medication. The inventory must prioritize conditions likely to occur, dangerous emergencies, and drugs that can serve several purposes. In the future, certain compounds may be produced through microorganisms or synthetic biology, but the earliest missions will still depend mainly on medication transported from Earth. When choosing a drug, the medical officer must also consider side effects and the condition of a body altered by spaceflight. Changes in fluid distribution, muscle mass, and liver or kidney function may affect how medication is distributed or removed. A familiar dose used on Earth may not necessarily produce exactly the same result after months in microgravity and Martian gravity. This is another area in which more real-world data is still needed. If the condition becomes serious enough to require surgery, the difficulty increases rapidly. Martian gravity still pulls blood and instruments downward, so an operation would not be identical to surgery in microgravity. The larger challenges, however, would be the lack of a full medical team, limited specialized equipment, a restricted blood supply, and the difficulty of providing intensive postoperative care. An operating room on Earth includes a surgeon, an anesthesiologist, nurses, and many other supporting professionals. Inside a small base, only a few crew members would have to divide all of those responsibilities while continuing to maintain the systems, keeping everyone alive. The medical officer might perform the procedure, another person could monitor anesthesia, and someone else would prepare the instruments. At the same time, air, water, and electrical systems would still require supervision. Stored blood presents a particular challenge because it has a limited shelf life and strict storage requirements. Crew members may be selected partly for their ability to donate blood to one another, but drawing blood from a healthy person also reduces the strength and capacity of the group. In a small community, every medical emergency affects not only the patient but also the number of people still able to keep the base operating. After surgery, the patient may be unable to work for days or weeks. Another crew member would need to spend time providing care, changing dressings, monitoring for infection, and assisting with movement. A single illness could therefore temporarily remove the working capacity of 2 or 3 people. In a crew of only 4 or 6, that change would be enough to force the entire mission schedule to be rebuilt. Infection can still occur even when the habitat is carefully controlled. Before launch, the crew undergoes medical screening and measures are taken to limit the introduction of new pathogens. Yet the human body naturally carries vast numbers of bacteria on the skin, in the mouth, and throughout the digestive tract. When an injury occurs or immune function changes, even normally harmless microorganisms can begin to cause problems. A sealed environment causes the same small group of people to continuously share air, surfaces, and equipment. A disease-causing bacterium could spread through hands, tools, or the water system if hygiene procedures are not thorough enough. The ability to culture samples and identify the organism would help the medical officer choose a more appropriate antibiotic. Using the wrong medication would not only waste valuable time, but could also contribute to antibiotic resistance. The supply of antibiotics would be limited, so they could not be used broadly for every symptom. An unnecessary course of treatment today might reduce the amount available for a more serious situation in the future. This would force the crew to balance early treatment against preserving their reserves. On Mars, managing medication would resemble managing water and electricity because every resource would be finite. Dental health is easy to overlook, yet it could become a serious concern during a mission lasting many years. A cracked tooth, an inflamed dental pulp, or an infection could cause severe pain, disrupt sleep, and make eating difficult. On Earth, the patient could simply visit a dentist. On Mars, the crew would need the ability to place temporary fillings, treat infections, and perform certain basic procedures themselves. Dental examinations and treatment before launch would reduce the risk, but they could not guarantee that every possible problem had been eliminated. The longer the mission continued, the greater the chance of cavities, fractured teeth, or gum disease. Dental tools would have to remain compact, and at least several crew members would need training in how to use them. A small pain inside the mouth could eventually reduce the effectiveness of the entire mission. An injury outside the base would create a different kind of emergency. A fall in low gravity could cause a sprain, a broken bone, or a collision between the suit and a sharp rock. If the injured person could no longer walk, the rest of the crew would have to bring them back to the airlock while everyone remained inside bulky suits. Dragging a body with considerable inertia across uneven terrain would not be simple, even though its weight had been reduced. Spacesuits and vehicles would need rescue attachment points so that an injured person could be pulled or secured without damaging the pressure-retaining layers. The rover would need to carry first aid equipment, backup oxygen, and a way to position someone horizontally while protecting their life support system. These situations would have to be practiced in advance, because once an accident occurred, the crew could not wait for step-by-step instructions from Earth. Moving an injured person through the airlock would present another challenge. A space originally designed for someone standing upright and moving normally might not accommodate an unconscious patient. Doors, floors, and connection points would need to allow a stretcher or towing device to pass through. If rescue requirements were not considered during the design stage, a person might be brought all the way back to the entrance and still be unable to enter quickly enough. Daily health monitoring could help identify problems before they became emergencies. Wearable sensors might record heart rate, sleep, physical activity, temperature, and blood oxygen levels. Small changes lasting several days sometimes appear before a person begins to feel ill. Long-term data would also help distinguish what was normal for each individual from a truly unusual sign. Continuous monitoring, however, would raise questions about privacy. If every heartbeat, sleeping hour, and location were recorded, the people inside the base might feel that their bodies were always being evaluated. The data would be necessary for safety, but not everyone would need access to every detail about another person. The community would have to establish clearly who could view the information, and under what circumstances the system was permitted to issue an alert. An unusual health reading would not necessarily mean that someone was unable to work. If the data were applied too rigidly, astronauts might hide symptoms because they feared being removed from their duties. On the other hand, if privacy were placed above every safety concern, the group could miss an important warning sign. A procedure balancing both sides would need to be agreed upon in advance, before anyone was placed under severe stress. Psychological health could not be separated from physical health. NASA has used simulated environments to study how people respond to long periods inside confined spaces. Hera covers approximately 650 square feet and has been used for simulated missions lasting up to 45 days. That small environment allows researchers to study sleep, performance, communication, and the way groups manage demanding work schedules. Chapia uses Mars Dune Alpha, a simulated habitat covering about 1,700 square feet, where groups of 4 people live through missions lasting nearly a year. They perform simulated tasks, manage resources, respond to equipment failures, and live with communication delays designed to resemble those of a Mars mission. These studies help researchers better understand stress, isolation, and long-term cooperation. Even so, no simulation on Earth can reproduce the complete experience. Hera and Chapia cannot create Martian gravity, the radiation environment of Mars, or the knowledge that an immediate return is impossible. Participants still know that hospitals, families, and the outside world remain relatively close. The results are therefore valuable, but they are not a complete replica of life on the Red Planet. The Martian cycle of day and night is relatively close to Earth's. A Martian day, commonly called a sol, lasts about 24 hours and 39 minutes. The difference of less than 40 minutes is enough for schedules to drift gradually away from Earth time, but the human body may adapt through changes in lighting and daily routines. It would not necessarily create a permanent state of jet lag. The greater difficulty would come from machinery noise, changing work schedules, and emergencies that interrupt sleep. Fans, pumps, and filtration systems could never be completely shut down at night. A quiet sound continuing for months might become exhausting even if it was barely noticed at first. When an alarm sounded at midnight, the body might need several days to return to a stable sleep rhythm. Lighting inside the habitat would need to change throughout the day to support the biological clock. Brighter light in the morning would help the body become alert, while softer light in the evening would signal that it was time to rest. If the base used the same level of illumination at every hour, sleep and mood could be affected. Lighting design would therefore be part of healthcare rather than simple decoration. Growing areas, images of nature, and familiar sounds could also reduce the sense of monotony. Humans evolved in environments filled with colors, scents, movement, and distance. Inside the base, the view would usually be limited by nearby walls, while most sounds would come from equipment. After many months, this lack of sensory variety could create a form of fatigue that was difficult to recognize. An area filled with plants would allow the eyes to rest on irregular shapes and observe changes unfolding over time. The scent of leaves, the humidity, and natural colors would provide signals that screens could never completely replace. These elements would not cure illness or remove stress, but they could make the living environment better suited to a brain that developed on Earth. Conflict within the group would often begin with very small things. Noise while someone was trying to sleep, the habit of leaving objects in the wrong place, the division of work, or the amount of water used for personal routines could become irritating through repetition. In a large environment, people could avoid one another for a while. Inside a small base, they would still have to eat, work, and respond to emergencies together. Even carefully selected people could disagree. Good teamwork during training would not guarantee that they would react the same way after months of sleep loss, isolation, and responsibility for one another's survival. The base would need conflict resolution procedures, private rest periods, and access to psychological specialists on Earth. Communication delays would slow those conversations, but they would not make the support useless. Private space would remain important even when the total area of the habitat was limited. A small compartment with a closed door, headphones, or a period without interruption could help someone recover after a stressful day. Privacy would not be a luxury added only after every other need had been met. It would be part of the ability to live for years within a small community without allowing tension to accumulate. The loss of personal autonomy might become more intense when every activity was scheduled and monitored. Each person's location, health, work, and resource use could be recorded by the system. Some degree of observation would be necessary for safety, but survival should not automatically erase every individual right. The community would need to define those boundaries before pressure began changing the way people treated one another. The abdominal pain that began at midnight might ultimately prove to be a minor problem. After examination, monitoring, and a response from Earth, the patient might rest, take medication, and return to work within a few days. Yet the entire event would reveal how distance had changed the meaning of healthcare. A familiar symptom would become a test of the base's equipment, knowledge, medical supplies, and ability to work together. A mission lasting several years could select healthy adults, screen them carefully, and train them for many possible situations. Although risks would remain, their bodies would already be fully developed, and a return journey would still exist within the mission plan. A truly permanent community would raise an entirely different question, because not every resident would be someone who had voluntarily left Earth after a careful selection process. That change would begin on the day a child was born beneath the red sky. This body would not merely have to adapt to Mars for a few years. It would develop from the beginning within higher radiation, enclosed spaces, and gravity only 38% as strong as Earth's. The question would no longer be whether a healthy adult could survive a mission, but whether the entire process of human development could unfold safely on another world. One day, a sound never before heard on any world beyond Earth may echo through a Martian base, the cry of a newborn child. From that moment on, this place would no longer be merely a research station for carefully selected adults. It would have become the home of a human being who never chose where they would be born. This image is often presented as the natural next step after humans establish a permanent base. Yet there is an enormous distance between keeping a group of astronauts healthy for several years and raising a child from the earliest stage of embryonic development. Science still does not know how pregnancy, childbirth, and the entire course of childhood development would unfold under elevated radiation and gravity only 38% as strong as Earth's. No human has ever been pregnant in deep space, nor has anyone completed an entire pregnancy in microgravity or given birth under partial gravity like that found on Mars. Most of what we currently know comes from cells, cultured tissues, short-term studies, and animal experiments. These provide important clues, but they cannot yet offer a definite answer for the human body. Space research agencies still regard reproduction, embryonic development, placental function, childbirth, and effects across multiple generations as major gaps in knowledge. Even on Earth, pregnancy is a complex process containing many sensitive stages. When higher radiation, an enclosed environment, and a level of gravity humans have never experienced for long periods are added, the uncertainty becomes even greater. Studies involving mice, fish, insects, and different types of cells have shown that gravity and radiation can affect cell division, gene expression, and tissue formation. Human pregnancy, however, lasts much longer, while the development of the brain, immune system, and placenta is considerably more complex. A result observed in an animal cannot automatically be turned into a prediction about a human child. It would therefore be wrong to claim that a child born on Mars would inevitably have birth defects, just as it would be wrong to say that development would certainly proceed normally. The most honest answer is that the available evidence remains insufficient. Animal experiments help identify which questions must be studied first. but they should not be used to write the future of a generation that does not yet exist. One of the clearest concerns is radiation. Embryos and fetuses contain many rapidly dividing cells, and certain stages of organ formation are especially sensitive to DNA damage. On Earth, the developing child is protected by the mother's body, the atmosphere, and the planet's magnetic field. On Mars, the last two layers of natural protection are far weaker. Living quarters for a pregnant resident might need to be located deeper inside the base, surrounded by water, supplies, and a thicker layer of Martian soil than ordinary living areas. Time spent working on the surface would almost certainly have to be restricted. Warning systems for solar energetic particle events would also need to prioritize moving the pregnant resident into the safest area as early as possible. Even then, there is no direct evidence from which to calculate rates of miscarriage, birth defects, or developmental disorders under Martian conditions. Any precise figure would be speculation unless supported by real observations. What science can say is that developing cells require greater protection, while the amount of shielding needed still demands further study. Low gravity introduces another group of questions. Even on Earth, pregnancy changes circulation, fluid distribution, heart function, and the mechanical load on the mother's bones. Under 0.38 g, the body may adapt differently, but we do not know how that adaptation would affect the placenta or the flow of blood reaching the fetus. Gravity also provides mechanical signals that help cells and tissues orient themselves during development. Bones, muscles, blood vessels, and many organs do not grow only according to genetic instructions. They also respond to the forces acting upon them. A level of 0.38 g may be sufficient for some processes, but not for others. Science does not yet have the evidence needed to locate that boundary. Any differences that develop may not be obvious at birth. A child could appear healthy at first while developing differently in the skeletal, cardiovascular, or nervous systems over many years. Conversely, some bodily adjustments might be entirely appropriate for the Martian environment and cause no illness there. Difference does not automatically mean damage. This uncertainty is precisely why childbirth cannot be treated as the simple next step after building a base. Having enough oxygen, water, and food addresses only the most basic conditions of survival. A community would need a far deeper understanding of reproductive health, prenatal care, and the treatment of complications before the birth of a child could be considered evidence of long-term success. Childbirth on Earth sometimes requires rapid intervention even after a completely normal pregnancy. Hemorrhage, infection, placental complications, or fetal distress can turn a routine delivery into an emergency. A Martian base would have no large blood bank, specialized surgical team, or fully equipped neonatal intensive care unit nearby. The community would need monitoring equipment, medication, surgical capability, and at least several people with advanced training in obstetric care. This would greatly increase the scale of the medical system. A clinic sufficient for adult astronauts might not be able to manage a difficult delivery, especially when the medical officer was also responsible for many other tasks. Deciding when the base was capable of supporting pregnancy would not be only an engineering question. It would also directly involve personal autonomy. A community might need medical guidelines based on the available level of safety, but those guidelines should not easily become absolute control over the bodies of its residents. After birth, an infant would require a far more stable environment than an adult. Temperature, nutrition, sleep, and air quality would need almost continuous monitoring. A small change that an adult could tolerate might affect a developing body much more strongly. A base originally optimized for work and scientific research would have to be redesigned as a place where children could be raised. The sounds of fans, pumps, and alarms that became ordinary background noise for astronauts might interfere with an infant's sleep. Lighting would need to follow a clear day and night rhythm, while the environment would have to remain safe for crawling, standing, and exploration. Technical surfaces, exposed wiring, and sharp edges suitable for adults might not be appropriate for a small body learning how to move. The need for privacy would also change. Feeding, caring for a child, and resting would require areas separated from shared workspaces. A base might be safe in terms of pressure and air quality, while still being unsuitable for psychological development. The ability to survive does not necessarily mean living in a nurturing environment. A child's musculoskeletal system raises an especially important question. On Earth, children develop muscles, bones, and movement skills as they crawl, stand, run, and fall under the pull of 1G. Every step places mechanical stress on the bones, helping shape their density and structure throughout growth. On Mars, those forces would be only a fraction of what the human body evolved to experience. Children might begin walking earlier or move in different ways because their bodies felt lighter. Their falls would also involve less force, but their bones and muscles would receive less stimulation at the same time. No one knows whether 0.38G would be enough to build a healthy skeleton for an entire lifetime. This question is even more difficult than preserving the bones of a fully grown astronaut. Play areas could be designed to increase mechanical loading through elastic cords, inclined surfaces, or activities requiring greater physical effort. A centrifuge might also create stronger gravity for short periods. Yet there is no evidence showing how much time a child would need near 1G, at what age exposure should begin, or whether the method would be safe enough. A centrifuge designed for children would also have to address dizziness, differences in force between the head and feet, and the risk of injury. Equipment suitable for an adult could not automatically be used by a young child. Artificial gravity might eventually become part of healthcare, but it is not yet a proven solution. The inner ear and balance system also develop through experiences early in life. The brain learns to combine signals from the eyes, muscles, joints, and vestibular organs to understand which direction is up or down and how the body is moving. A child growing up under 0.38G might build a frame of reference perfectly suited to Mars. They might run, jump, and balance easily in that environment, even if their movements differed from those of children on Earth. What remains unknown is how the body would respond under the pull of 1G. There is no evidence proving that someone born on Mars would be unable to stand or walk on Earth, but adapting could require considerable time and medical support. Before traveling to Earth, that person might need to increase mechanical loading gradually through centrifuges or specialized exercise equipment. The spacecraft might also provide artificial gravity during part of the journey to help prepare the body. The chances of success would depend on age, health, the length of time spent under 0.38G, and how much capacity for adaptation the body still retained. A child's immune system, meanwhile, needs an environment that is both clean and sufficiently diverse. Human beings do not grow up in isolation from microorganisms. The microbial communities on the skin, inside the digestive tract, and throughout the surrounding environment help train the immune system and support digestion. A Martian base would contain far fewer microbial species than Earth and would regulate them much more carefully. An environment with too little microbial diversity could affect the way the immune system matures, yet allowing bacteria and fungi to grow without control would also be dangerous. The community might need to actively maintain a healthy microbiome within food, plant growing areas, and living spaces. This would be very different from simply sterilizing every surface until almost nothing living remained. Breast milk, fermented foods, and carefully monitored microbial communities could all play important roles, but no one yet knows which combination would be best for a generation living beyond Earth. The microbial ecosystem inside the habitat would also change over time, influenced by medications, cleaning products, and waste treatment methods. Raising a child would mean managing not only one human body, but also the microbial environment surrounding it. The natural world familiar to that child would be very different as well. They could not open a door and step into a meadow, onto a beach, or beneath a forest canopy. Beyond the glass would lie red soil, radiation, and an atmosphere that could not be breathed. Their closest experiences of nature might be a greenhouse, a small pool of water, virtual environments, and recordings sent from Earth. Green spaces would therefore hold value far beyond the amount of food they produced. They would be where a child could watch leaves unfold, roots grow, and another living organism respond to light. Plants would help them understand that life did not exist only inside the human body or behind a screen. A growing area large enough to explore might become the first park in a Martian community. Yet a simulated experience is not entirely the same as nature itself. Virtual reality could display an ocean, but it could not fully reproduce the smell of salt, the wind, or the sensation of open space stretching all the way to the horizon. A child might know a great deal about Earth through images and still never fully understand what it feels like to stand in the rain or walk barefoot across damp soil. This would not necessarily make childhood less meaningful, but it would create a different culture. Stories of oceans, forests, and blue skies might carry the same emotional weight as legends of a distant homeland. Earth would be both a real place and a world most Martian children knew only through the memories and stories of others. Education in a small community would also need to be organized differently. If the population included only a few dozen or a few hundred people, there could not be a specialized teacher for every subject. Adults in the habitat might teach the fields they understood, while other lessons relied on stored courses, intelligent learning tools, and educators on Earth. Communication delay would not prevent learning, but it would make a live classroom difficult. A question sent to a teacher might not receive an answer for dozens of minutes. Students would need to become comfortable researching independently, recording their questions, and continuing to work while they waited. Essential educational materials would have to be stored inside the habitat so that a loss of communication could not bring the school to a stop. The education system would also need to pass on survival skills such as repair work, medicine, and resource management. Yet if every lesson focused only on maintaining the base, children might grow up believing that their value was determined entirely by the work they would perform in the future. A sustainable community would need to teach art, history, music, and subjects that did not directly produce oxygen or water. Friends of the same age would be difficult to replace with technology. Children learn to share, disagree, and cooperate by playing with many different people. In a community with very few children, every relationship might carry greater pressure because there would be fewer social groups to choose from. Even a minor conflict would be harder to resolve by simply finding a different circle of friends. Population size, therefore, could not be calculated only in terms of beds, oxygen, or food production. Psychological health would require enough variety in ages, personalities, and social roles. A community might possess sufficient resources for 10 children and still fail to provide a healthy social environment if those children were widely separated in age or had almost no peers at the same stage of development. As they grew older, each person might be expected to take over a necessary role. If the base lacked doctors, a child with strong academic abilities might be guided toward medicine even if they dreamed of becoming an artist. The needs of the community would be real, because the absence of one specialist could endanger many lives. But personal choice could not be treated as a luxury. A society that existed only to keep machinery running would risk turning human beings into biological components. Each person would be valued according to their ability to repair pipes, care for crops, or treat illness. Without room for art, personal interests, and different ways of living, the community might survive technically while remaining profoundly impoverished in spirit. A similar problem would emerge around reproduction. In a small population, the number of children born, the timing of births, and the level of genetic diversity would all become important questions. A community could not increase its population faster than its ability to provide air, water, and medical care. But turning those calculations into the power to force reproduction or prohibit it entirely would violate human dignity. There is no single minimum population that guarantees every small community will survive across many generations. The requirements would depend on age, structure, sex ratios, the degree of exchange with Earth, and the length of isolation. Banks of embryos, sperm, or eggs might help increase genetic diversity without requiring an enormous population to be transported to Mars from the beginning. Those methods would create new questions of their own. Who would own and manage the genetic material, who would be allowed to use it, and how much right would the people born from it have to know their origins? These decisions could not simply be handed over to a computer. Biological solutions always carry medical, legal, and ethical responsibilities. The possibility of traveling to Earth would also directly affect personal freedom. Someone born on Mars might one day want to visit the planet their parents or ancestors had left behind. There is no evidence that they would certainly be unable to live under 1G. However, the journey might require far more preparation than it would for an adult astronaut raised on Earth. Exercise equipment, artificial gravity environments, and medical care might help the body adapt gradually. The spacecraft would also need to be designed so that the traveler was not forced to move abruptly from 0.38 g into microgravity and then down into 1 g. The ability to return would depend not only on personal determination, but also on the technology the community could provide. Across many generations, the different environment might create evolutionary pressures. Traits better suited to low gravity, radiation, or enclosed spaces could influence health and reproductive success. Yet this does not mean humans would inevitably or rapidly become a separate species. Evolution does not follow a simple timetable. Medicine, technology, choice of partners, and continued population exchange with Earth could all alter natural selection. If people actively used medication, shielding, and artificial gravity, the biological environment actually acting upon their bodies would be very different from the natural conditions of Mars. The ability to give birth to a child would therefore not automatically prove that the community was sustainable. The more important question would be whether that child could grow up healthy, receive an education, have friends, and possess the freedom to choose their own life. Biological survival would be only the first layer of a society worth living in. A base could maintain perfect pressure and still fail if children grew up without privacy, without any path beyond assigned occupations, and without the ability to leave. A true community would need to protect the bodies, minds, culture, and dignity of people who had never chosen the world into which they were born. The first cry beneath the red sky would be a remarkable achievement, but it would also bring an unprecedented responsibility. From that moment on, every decision about resources, medicine, and government would affect more than the adults who had voluntarily joined the mission. It would affect a generation entitled to more than the bare minimum required for survival. Even if every biological question gradually found an answer, the community would still have to maintain its habitat for decades. Filters would age, pumps would wear down, medications would expire, and electronic systems would eventually fail. No shipment from Earth could be assumed to arrive forever. The birth of a new generation would therefore carry the story beyond biology. For Mars to become a true home, it would need not only people born there, but also the ability to create the things they would use throughout their lives. The real boundary lies between an inhabited base and a community capable of continuing even after supply ships no longer appear in the sky. The message arrives at the beginning of the work shift. The next supply shipment will be delayed. There is no explosion, no system stops functioning, and the reserves are still sufficient for many months. Yet the entire plan for the base must be recalculated. Medical supplies are inventoried, food is reorganized according to shelf life, spare parts are classified by importance, and equipment that is not immediately essential is temporarily shut down. The delay does not place anyone's life in immediate danger, but it reveals an important distinction. Humans may be able to live on Mars for a certain period using what has been prepared on Earth. Continuing to survive when spacecraft no longer arrive on schedule is an entirely different challenge. The distance between those two conditions cannot be crossed simply by adding a few more greenhouses or building a larger water reservoir. It requires an entire industrial system to be created from the ground up. The simplest form of human presence is an exploration outpost. A small group travels to Mars, lives there for a defined period, and then returns home. Most food, medicine, components, and equipment are carried with them or sent ahead. The base may extract some water, produce oxygen, and use robots for support, but it still depends heavily on a supply chain extending back to Earth. The next stage is a settlement capable of producing some of what it needs locally. Water is extracted from subsurface ice, oxygen is made from water or the atmosphere, and part of the food supply comes from greenhouses. Martian soil may be used for shielding, while simple components are manufactured in a workshop. Dependence on Earth is reduced, but it does not disappear. The final stage is far more difficult. A community capable of continuing to function when its supply chain is interrupted for an extremely long time. Not merely for a few months or a single launch window, but perhaps for years or even decades. Every failed device would then have to be repaired, recycled, or replaced with something produced locally. This is the distance so often missing from images of brightly illuminated Martian cities beneath enormous domes. Extracting water and producing oxygen would still not be enough to qualify as self-sufficiency. Water becomes drinkable only while pumps, filtration membranes, sensors, and chemical processors remain operational. Oxygen remains safe only while concentration monitors, compressors, valves, and pipelines continue to function without leaking. If one small chip inside a controller fails, a tank filled with water may become almost as difficult to use as the ice buried beneath the ground outside. A community may grow vegetables while still depending on lights, fertilizer, pumps, and sensors from Earth. It may be able to print a new handle while remaining unable to produce lubricant, bearings, or an electric motor. Self-sufficiency, therefore, cannot be measured only by the amount of raw material available. What matters more is the ability to replace the entire chain of equipment that transforms those raw materials into something humans can use. Consider a pump that appears simple. To manufacture it, the community would need sufficiently durable metal, wiring, magnets, seals, lubricants, bearings, and a control unit. These parts would have to be cut, cast, machined, and measured to the necessary precision. To build the machine tools required for that work, the settlement would need even larger equipment, better materials, and people trained to operate them. The problem is not that Mars completely lacks the necessary elements. Its rocks and soil contain iron, silicon, aluminum, magnesium, and many other materials. The difficulty lies in extracting them, separating them from minerals, removing impurities, and producing materials with stable properties. A metal beam used for structural support may tolerate significant variation, but a bearing expected to rotate for thousands of hours requires a far more precise surface and composition. Refining metals requires high temperatures, chemicals, electricity, and equipment capable of surviving harsh conditions. Producing electrical wire demands highly purified conductive metal and durable insulation. Manufacturing magnets, optical glass, or filtration membranes requires entirely different processes. The more the base attempts to manufacture for itself, the more layers of industry it must build behind every finished product. Electronics would be among the most difficult dependencies to eliminate. Computers and sensors appear in nearly every system, from atmospheric control to health monitoring. Yet producing modern computer chips requires extraordinarily complex factories, clean environments, many highly purified chemicals, and machinery capable of extreme precision. This is not a technology that can be recreated with a small workshop and a few printers. Over time, a Martian community might learn to repair circuit boards, replace components, and recover useful parts from old equipment. Life-critical systems could also be designed with simpler electronics that are easier to maintain. Even so, many precision sensors, memory devices, and processing chips would probably still need to come from Earth. Each shipment would carry not only physical supplies, but also the most sophisticated products of the industrial world left behind. Pharmaceuticals would create another source of dependence. Some simple compounds might be synthesized locally, while engineered microorganisms could produce certain vitamins or proteins. But a complete range of medicines, vaccines, laboratory chemicals, and medical supplies would require a much larger research and manufacturing infrastructure. Producing an active compound does not automatically mean producing a safe medication. Every drug must be tested for purity, dosage, stability, and contamination. Chemical analysis equipment must remain calibrated, and the manufacturing process must produce consistent results each time it is repeated. A small community would struggle to maintain this entire network for hundreds of different medications. During the first many years, its medical supply would remain deeply dependent on Earth. Medical independence would also require far more than medicine. The community would need the ability to diagnose illness, train physicians, maintain equipment, and preserve knowledge across generations. A clinic filled with instruments would become meaningless if no one knew how to use them. When someone with specialized skills could no longer work, the loss might be more serious than the failure of any single machine. Knowledge, therefore, becomes a life-sustaining resource. Technical, medical, scientific, and cultural information must be preserved in several forms. Digital data is easy to copy and occupies little physical space, but it depends on electricity, reading devices, and software. Printed books can survive many conditions, yet they are heavy, require storage space, and remain vulnerable to fire and moisture. No method of preservation is safe enough on its own. Data could be stored across several systems, kept in open formats, and checked regularly. Essential knowledge might also be printed on paper or more durable materials, so it could still be read after computers stopped working. Yet preserving information does not guarantee that future generations will understand it. A library containing millions of pages cannot replace education and practical experience. To repair a pump, a student must observe it, touch its components, and learn to recognize the sound it makes when something is wrong. To become a physician, a person must be guided through real medical cases rather than merely reading documents. Living knowledge passes through people, habits, and experience, not only through stored files. In a small community, one person may hold much of the available knowledge about electrical systems, crops, or medicine. If that person becomes ill, dies, or can no longer work, the settlement loses an important part of its capability. Cross-training can reduce the danger, but no one can become a deeply qualified expert in dozens of fields at once. Time available for learning is itself a limited resource. Large societies on Earth function through the specialization of millions of people. Some refine metals, others build machines, develop medicines, or teach. No individual needs to understand the entire system because people exchange products and services with one another. A small Martian community would not have access to such a vast network, forcing it to choose between deep specialization and the ability of its members to replace one another. A growing population would expand the number of professions and the degree of specialization possible. More doctors could cover a wider range of medical fields, while more engineers could maintain increasingly complex industries. Yet every new person would also require air, water, food, space, and medical care. Population growth would solve certain problems while placing greater demands on resources. Local materials could reduce some of the burden of construction. Martian soil might be compressed, fired, or mixed into materials for walls and protective shielding. Construction robots could prepare foundations, stack blocks, or print large structures before humans arrived. A thick layer of soil around the base would both reduce radiation exposure and help stabilize temperature. But the walls would not be the entire house. Martian material would not automatically become airlocks, pressure seals, electrical wiring, pipes, or filters. Inside, every module would still be a mixture of metals, plastics, glass, elastomers, and electronic equipment. The ability to build the outer shell locally would be an important step, but it would address only the heaviest and most visible part of the structure. Every new module would also need to be connected to the air, water, electrical, and data networks. As the base expanded, the number of valves, joints, and potential leak points would increase. A larger system would provide more space and redundancy, but it would also create more places where failure could occur. Expansion could not be achieved simply by attaching another room to the end of a corridor. A modular design would allow each section to operate independently or be sealed off when necessary. If a pipeline leaked, the rest of the habitat could retain pressure. If one power station failed, other sources could continue supplying electricity to the essential living areas. The entire community should never depend on a single valve, cable, or pump. Transportation would expand the range of resource extraction while also increasing risk. Rovers carrying people and cargo could reach distant ice deposits, mineral sites, or research areas. But there would be no repair stations along the way and no rescue team nearby. Every journey would need enough oxygen, battery power, spare parts, communications equipment, and a way to return if the primary vehicle failed. Building secondary bases could reduce travel distances and provide shelters along important routes. Yet every new location would require energy, maintenance, and inspection. A wider network would not automatically be safer if resources were spread too thinly. In some cases, one concentrated and carefully maintained settlement might be far more reliable than several small outposts separated by great distances. The Martian economy would also be unlikely to depend on images of spacecraft carrying valuable minerals back to Earth. Transporting large quantities of material through space requires enormous amounts of energy and time. If the value of the cargo were lower than the cost of lifting it from the surface and delivering it to Earth, the activity could not remain sustainable simply because the material appeared rare. Early economic activity would more likely focus on science, technology testing, and services connected to exploration. Knowledge gained from operating closed systems, recycling water, using autonomous robots, and farming under extreme conditions could hold considerable value. Information is easier to transmit through space than matter, so the most important product of the outpost might be data and experience. Money, private ownership, and paid labor might continue to exist, but they would have to adapt to a very different reality. Air, water, and electricity are not ordinary commodities because their absence could kill people within a short period. If one person owned the entire oxygen supply, that ownership would become direct power over the lives of everyone else. Some resources might therefore need to be managed as shared infrastructure, even if the settlement preserved private activity in other areas. The community would have to decide who received priority when electricity declined, who was responsible for maintenance, and what happened when someone used more than their share of a limited resource. Economic questions would quickly become ethical and political ones. During an emergency, the base would need a clear chain of command. When pressure was falling or a fire had started, there would be no time for a prolonged debate before closing a valve. Yet authority exercised during a few dangerous minutes would not necessarily need to become control over every part of daily life. The community could distinguish between emergency command and long-term government. Rules would need to be created before a crisis occurred. Resource distribution, privacy protections, dispute resolution, and leadership succession should be agreed upon while everyone was still calm. If the rules appeared only after water supplies began to decline, the person controlling the machinery could easily become the person who controlled every decision. Government on Mars would also be shaped by the distance from Earth. A remote authority could not respond immediately to every situation. The community would need enough autonomy to manage conditions on the ground while still remaining bound by broader agreements. The boundary between self-government and responsibility to humanity would not be simple. That responsibility would be especially clear in the matter of planetary protection. Humans carry enormous numbers of microorganisms on their skin, inside their bodies, and across their equipment. No matter how strict the cleaning procedures became, it would be impossible to eliminate every organism traveling with them. As the base continued operating, terrestrial bacteria would appear in the air, wastewater, and on many surfaces. This would make the search for native life more difficult. If microorganisms were found in a soil sample, scientists would need to determine whether they came from Mars or were simply contamination from the base. NASA and other research organizations continue developing planetary protection requirements for human missions, including the risks of carrying Earth organisms to Mars and returning Martian material to Earth. Some regions might be considered especially sensitive for scientific reasons. If any location contained temporary liquid water or conditions more favorable to microorganisms, human activity nearby might need to be restricted. Rovers, drills, and people could be required to avoid those areas or follow much stricter procedures. The ability to extract a resource would not automatically create the right to use it. This could create a genuine conflict between survival and exploration. An easily accessible source of ice might lie near an area that needs to be protected. The community would have to choose between lowering the cost of sustaining itself and preserving the scientific value of that location. If native life exists, contaminating the environment could destroy the opportunity to study a biological origin entirely independent of Earth. Mars is often described as a dead world, but that phrase should be used carefully. No evidence has confirmed life there today. Yet the possibility of microorganisms surviving beneath the surface has not been completely ruled out. The planet does not possess a rich surface biosphere like Earth's, but it still has climate, ice, dust, weather, and ongoing geological processes. Even if Mars contains no life, it still preserves the history of a world that once had rivers, lakes, and wetter environments. Every layer of rock may hold information about how the planet changed over billions of years. Building a community there would not simply mean occupying empty land. It would mean entering a scientific archive that has not yet been fully read. The idea of transforming the entire planet often appears as the ultimate solution. One common proposal is to release carbon dioxide trapped in the soil, ice, and minerals, thickening the atmosphere and creating a stronger greenhouse effect. However, research by Bruce Jakosky and Christopher Edwards found that the accessible carbon dioxide on Mars is not sufficient to produce substantial atmospheric pressure and warming with present-day technology. This conclusion does not mean that every possible form of planetary engineering in the future would violate the laws of physics. It only shows that a plan relying mainly on the carbon dioxide already available cannot turn Mars into a second Earth using current capabilities. The amount of gas that could be mobilized is far too small compared with what would be required to create a dense atmosphere. Even if the planet were warmed and its pressure increased, the air still would not be breathable. An atmosphere made mostly of carbon dioxide does not become oxygen simply because it grows thicker. For humans to walk outside without pressure suits, the composition of the entire atmosphere would have to change on a planetary scale. That task would be far greater than merely raising the temperature. Radiation would not disappear simply because the surface became somewhat warmer. Water would have to remain stable, the soil would need nutrient cycles, and the climate would have to persist over extremely long periods. If the atmosphere continued escaping into space, every effort to transform the planet would require constant replenishment. Terraforming is not a single switch, but a series of interconnected problems. A more realistic approach would be to transform individual enclosed regions. Instead of changing the entire planet, humans might create domes, tunnels, or covered valleys. Inside them, pressure, temperature, and atmospheric composition could be controlled. Living spaces could grow far larger than the original base without requiring the transformation of all Mars. This approach is often called paraterraforming. It reduces the scale of the challenge and allows expansion to happen gradually. One enclosed region might contain plants, water, and enough open space for people to move more freely. Yet, the outer shell would still have to remain airtight. Machinery would still have to regulate the atmosphere, and the entire system would still need electricity. Humans would still be living inside an artificial environment, only one that was larger and more complex. A vast dome might feel closer to an open landscape, but any crack or structural failure would still need to be detected. As the enclosed area expanded, the amount of surface requiring maintenance would grow with it. Paraterraforming would not eliminate dependence on technology. It would simply expand that technology from the scale of a room to the scale of a neighborhood. The idea of Mars as a backup planet must therefore be viewed with caution. For the foreseeable future, every settlement would continue to depend on technology, knowledge, and at least part of Earth's industrial system. If civilization on the home planet suddenly lost the ability to provide support, a Martian community would also face severe danger. Distance alone would not make it independent. Mars could expand the reach of human civilization and preserve some knowledge and culture from regional disasters, but it could not easily replace Earth's entire biosphere, industry, and population. Our home planet provides more than air and water. It contains a network of billions of people, along with ecosystems and factories that a Martian base would struggle to recreate even in very small fragments. These limitations do not make exploration meaningless. The effort to live on Mars could advance water recycling technology, remote medicine, autonomous robotics, reliable energy systems, and closed-environment agriculture. Many solutions developed for such an extreme setting could also support regions on Earth where resources are scarce. A scientific outpost would remain valuable even if it never became a self-sufficient city. It could study the planet's climate history, search for biological traces, and help humanity understand the limits of the body beyond Earth. Exploration does not need to be justified by promises that millions of people will soon move there. Understanding another world is already a worthy goal. As technology matures, humans may be able to establish bases while accepting an appropriate level of risk. Over time, a larger settlement might emerge, produce more of its own resources, and gradually reduce its dependence on Earth. But there would be no single moment when the base suddenly became an independent civilization. The transformation would happen one component, one skill, and one generation at a time. The distance between an outpost and a self-sufficient community may be greater than the physical distance between Earth and Mars. It is a distance measured in metallurgy, chemistry, electronics, medicine, education, population, and government. Every field would require time to develop, and weakness in one link could place many other systems under strain. The delayed shipment is eventually incorporated into the new plan. The base reduces certain research activities, extends the service life of spare parts, and devotes more greenhouse space to nutrient-rich crops. No one panics, because the reserves remain sufficient and the spacecraft has not been canceled. Yet everyone understands that their lives are still connected to Earth by an extraordinarily long route. After a day of inventories and calculations, an astronaut stands beside a window and looks across the red plain. Outside, there are no trees, rivers, or signs of a city. Only rock and soil stretch toward the horizon beneath a pale sky. Behind them, the ventilation fans continue their steady sound, moving the same volume of air through the filters once again. The base glows in the desert like a small island. Inside it are recycled water, gases produced by machines, seeds carried from Earth, and a store of knowledge preserved across many servers. Everything required for life is present, yet none of it exists naturally. The island must be cared for hour by hour so that it is not swallowed by the silent red ocean surrounding it. Perhaps one day, many settlements will be connected, greenhouses will grow wider, and workshops will produce most of the equipment their communities require. But in the dim light of the first base, the truth remains unmistakably clear. Humanity has not brought an entire civilization to Mars. It has carried only a very small piece of Earth and is trying to keep that piece alive. Sunset is settling over the Martian plain. Through the fine dust suspended in the atmosphere, the sky around the sun takes on a pale blue glow, while the more distant regions gradually deepen into dark red. Across a landscape so vast it seems almost without end, there is no city of connected domes. There is only a low habitat pressed close to the ground, as though trying to make itself smaller against the frozen desert. Through a small window, the final light of the day touches the walls and then disappears. The astronauts put away their tools, review the operating schedule, and prepare for sleep. No major failure has occurred. No one has been injured, and no system has issued a serious warning. It has been what might be called an ordinary day, although that sense of normalcy exists only because thousands of processes happened at exactly the right time. As the living quarters slowly grow dark, the most important parts of the base remain awake. Fans move air through the ducts, preventing oxygen and carbon dioxide from gathering in sealed corners. Filters continue removing waste gases from circulation. Sensors in every compartment compare pressure, temperature, and air composition against limits established long before. Water vapor leaves the body with every breath. Instead of disappearing, it is drawn toward a condenser, becomes tiny droplets, and enters the treatment system. A few days later, some of that water may return in a drinking glass, a meal, or the solution feeding the plants. The distance between a breath and a sip of water is only a chain of pumps, filtration membranes, and chemical reactions. At the same time, the central computer checks the remaining charge in the battery banks. An algorithm adjusts the speed of several devices to reduce nighttime power use, but ventilation, thermal control, and water processing must continue. The base can dim its lights, postpone research, or reduce power to the greenhouse. It cannot stop breathing. In the growing area, small leaves lean toward the lamps. They do not know that the sky above them is red, or that no rain is approaching beyond the walls. For the plants, the world consists only of light, water, carbon dioxide, temperature, and nutrients. As long as those conditions are maintained, life continues its familiar work. It is here that the true meaning of living on Mars becomes clear. The achievement does not end with a rocket powerful enough to cross hundreds of millions of kilometers, nor is it complete when the first human foot touches the red soil. The greater challenge is creating a small, stable cycle capable of preserving water, air, heat, and biology in an environment that does not naturally provide them. Behind the steady sound of the fans lies centuries of human knowledge. Chemistry makes it possible to separate oxygen and capture carbon dioxide. Biology teaches us how to grow plants, protect the body, and manage microorganisms. Materials science creates shells that can retain pressure, while electronics allow sensors to detect changes too subtle for humans to feel. Medicine is present in the stored drugs, ultrasound equipment, and emergency procedures preserved in the habitat. Psychology appears in the design of private spaces, lighting cycles, and work schedules. Electrical engineering connects every system to a shared source of power. The base survives not because of one extraordinary invention, but because countless forms of knowledge have been assembled with enough precision to work together. Even so, Mars has never been the enemy in this story. The planet does not become cold to drive humans away, release radiation to punish them, or create dust with the intention of damaging machinery. These conditions are simply the result of its thin atmosphere, geological history, and position within the solar system. The more vulnerable side of the encounter is the human body. Our lungs developed inside an ocean of air. Our bones grew under Earth's gravity, and our cells have spent their entire existence beneath a thick atmosphere and a global magnetic field. The body is accustomed to liquid water, abundant food, vast ecosystems, and countless microorganisms living alongside it. For that reason, humans cannot simply arrive on Mars and live directly from what the planet provides. Between the skin and the world outside, there must always be an intermediate layer. A pressure suit, radiation shielding, an oxygen production system, water purifiers, and an electrical network that never stops operating. If that layer weakens for too long, the technological distance between a safe room and the desert beyond will quickly disappear. For the foreseeable future, a Martian settlement will resemble an enormous spacecraft that has landed more than it resembles a new town on Earth. It will no longer be traveling between planets, but it must still recycle air, protect water, regulate heat, and monitor every system as though it were still in deep space. The only difference is that there is now solid ground beneath it. Those severe limits may force humans to learn how to use resources with far greater care. Nearly every drop of water must be recovered. Energy cannot be consumed without considering the needs of tomorrow. Waste must be treated as carbon, nitrogen, minerals, and water that have not yet returned to the right place. Nutrients may need to be produced when required, rather than stored without end. The solutions developed for Mars would not necessarily serve Mars alone. Water purification and recycling technologies could support drought-stricken regions. Compact, diagnostic equipment and remote medicine could reach communities far from hospitals. Closed-loop agriculture, autonomous robots, and resilient power systems could also be valuable in places affected by natural disasters or extreme environmental conditions on Earth. Seen from the red world, our home planet takes on a different meaning. There, air surrounds the body without fans forcing it through filters. Rain carries water from the sky to the ground, rivers move it across continents, and ecosystems help process waste without waiting for humans to open each valve. A field on Earth is nourished by more than water and sunlight. Beneath the surface, minerals, organic matter, fungi, and bacteria form a complex living network. The oceans store heat, the atmosphere carries moisture, and the magnetic field deflects many charged particles arriving from space. Most of these processes happen so quietly that humans easily take them for granted. Perhaps Earth is the greatest life support system we have ever known. It was not assembled in a factory, nor does it require a team of engineers to inspect it every morning. The planet had already been operating for billions of years before humans appeared, creating conditions in which water, air, and biology could join together into a habitable world. The imagined camera begins to pull away from the base. Its low walls gradually blend into the darkness, while the light from its windows shrinks into a single point on the plane. From far enough away, it resembles a star that has fallen onto the red ground and is still struggling to keep its light from fading. Inside that point of light is air that has been created and used again. Water has passed through bodies, plants, and sealed pipes before returning to storage. Seeds carry the history of evolution beneath Earth's sundae. The people living there still remember the color of the ocean, the smell of soil after rain, and the feeling of stepping outside without wearing a protective shell. Perhaps, at some distant time in the future, people will work, grow up, and be born on Mars, Small habitats may expand into communities, and growing chambers may become green spaces large enough for children to run between rows of leaves. Yet no matter how far they are from their home planet, Earth will remain present in every condition that keeps them alive. It will be there in every renewed breath, every drop of water that finds its way back, and every leaf that unfolds beneath artificial light. Mars may become a new home, but to live there, humanity will always have to carry a part of its first home along.